There are places in our universe where the laws of physics are pushed to their breaking point. Places where spacetime itself gets so warped, so bent, that reality as we know it just stops working. These aren't from science fiction. They are real, and they are out there, lurking in the dark. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. These are places where gravity, the force that keeps our feet on the ground, becomes an absolute tyrant. It gets so powerful, so concentrated, that it creates an edge in space from which nothing can ever return. Think of a waterfall with a current so strong that once you go over the edge, no engine, no rocket, nothing can pull you back. Now, imagine that current as gravity, and it's so strong it can even pull in light, the fastest thing in the universe. We call that edge the event horizon. It's the point of no return. It's a ghostly sphere hanging in the void, completely silent and invisible. Anything that crosses it, a rock, a planet, a giant star, is lost forever, pulled towards an infinitely dense center called a singularity. The iconic black circle we see in pictures is the shadow of this cosmic trap, a dark silhouette against the glowing, superheated gas swirling around it like water circling a drain. This is the abyss made visible. But here's where our intuition completely fails. You'd think something with that much gravity has to be impossibly enormous. And you'd be right. But you'd also be wrong. The story of black holes doesn't start with universe-swallowing giants, but with the death of a single star. A star much, much bigger than our sun lives out its life and dies in a massive explosion. Its core collapses under its own incredible weight, squeezing all that mass into a point of unimaginable density. And just like that, a black hole is born. This new object might have the mass of 10 suns, a staggering amount of stuff. But its event horizon, its physical point of no return, would only be about 60 kilometers across. You could hide it in a major city. This is where our journey begins, not a journey across space, but across scale. A cosmic safari to hunt the biggest monsters in the universe, each one more terrifyingly vast than the last. And to truly understand their size, we have to start with something we know. We have to start with our sun, the anchor of our world. Our sun is the anchor of our world. It's the source of all warmth, all light, and all life on Earth. From here, it looks like a perfect, brilliant disk in the sky, but its familiar face hides a scale that's already hard to wrap your head around. The sun is 1.4 million kilometers in diameter. You could line up 109 Earths, side by side, just to cross its face. If Earth were a small marble, the sun would be a giant exercise ball. You could fit 1.3 million Earths inside it. It contains over 99.8% of all the mass in our solar system. Jupiter, all the other planets, all the moons and asteroids. They're just cosmic dust bunnies by comparison. This magnificent star is our measuring stick. In the language of cosmic mass, it's 1 solar mass. This is our first step on a ladder of scale that is about to spiral completely out of control. But before we meet the real giants, we have to understand where they come from. Our sun will die one day, but it's not big enough to become a black hole. For that, you need a true stellar heavyweight, a star at least 20 to 25 times more massive than our own. These monsters live fast and die young, burning thousands of times brighter than our sun. When their fuel runs out, they don't go quietly. The outward pressure from nuclear fusion, which held them up for millions of years, vanishes in an instant. Gravity, which has been waiting patiently, wins a sudden, catastrophic victory. The star's outer layers are blown away in a supernova, an explosion so bright it can outshine its entire galaxy. But the core collapses inward, relentlessly. The crush is so complete that atoms are obliterated. All that matter, the mass of several suns, is packed into a space smaller than a molecule. A singularity. This is how the smallest, or stellar mass, black holes are born. And here's where the physics gets bizarre. Mass and size become disconnected. An object with the mass of a star can have the physical footprint of an asteroid. But these are just the newborns. Astronomers have found a mysterious middle class, known as intermediate mass black holes. They are the missing link. These can pack the mass of 100 to 100,000 suns. If our sun were a single grain of sand, a 100,000 solar mass black hole would be a hefty handful. Yet, its event horizon, the actual point of no return, would still be smaller than the radius of our own sun. Think about that. An object 100,000 times heavier than our sun, yet physically smaller. This is a stepping stone from the black holes we can almost comprehend to a class of objects so vast they anchor entire galaxies. We are now leaving the realm of the familiar. We are heading for the supermassive. The heart of our home. We live in the Milky Way galaxy, a sprawling city of stars. On a clear night, you can see it as a faint, milky band stretching across the sky, the combined light of billions of stars. Our solar system is just one of countless systems, tucked away in a quiet spiral arm, about 2/3 of the way out from the galactic center. Like almost every other big galaxy, the Milky Way has a secret at its heart. It has a monster. For decades, astronomers tracked stars whipping around an invisible point at the galaxy's center, a radio source called Sagittarius A, or SGRA* for short. They watched one star, S2, complete a full orbit in just 2 years, moving at incredible speeds. The only thing that could command that much gravitational force in such a small space was a supermassive black hole. The 2020 Nobel Prize in Physics was awarded for this very discovery. This is our supermassive black hole. It's about 26,000 light-years away, and its mass is around 2 to 3 million times the mass of our Sun. 4.3 million suns. If our Sun were a white blood cell, SGRA* would have the mass of a 190-kilogram person. In 2022, the Event Horizon Telescope collaboration released the first direct image of SGRA. We were finally looking our own monster in the eye. A fuzzy, golden ring of light swirling around a dark central shadow. So, how big is it really? The shadow of Sagittarius A is so large it spans about half the orbit of Mercury. But a better way to feel the scale is to imagine swapping our Sun with it. Suddenly, the center of our solar system would be a sphere of pure blackness 24 million kilometers across. You could line up 17 of our suns side by side inside its event horizon. This is the scale of the black hole in our own galaxy. It's massive enough to hold billions of stars in its gravitational grip, yet its size is something we can just about measure against our inner planets. It feels like a limit. It feels like the biggest thing that could possibly exist. But SGRA is not a monster. It's a kitten. We are about to enter the true gallery of giants, where our entire solar system becomes the new measuring stick. The Gallery of Giants. Our journey now takes us beyond the Milky Way. First stop. The galaxy Cygnus A, a powerful radio galaxy whose central engine is a supermassive black hole with a mass of 2.5 billion solar masses. Not million. Billion. That's nearly 600 times the mass of Sagittarius A. How do you visualize that? Forget Mercury. If we placed the Cygnus, a black hole, at the center of our solar system, its event horizon would swallow the Sun, Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Its edge, the point of no return, would lie somewhere out past the orbit of Uranus. Our entire solar system would be nothing more than a snack. And we're just getting started. Our next exhibit is maybe the most famous black hole in history. It lives in the center of Messier 87, a supergiant galaxy 55 million light-years away. In 2019, the Event Horizon Telescope released the first ever direct image of a black hole, and it was this one, M87. That picture was front-page news worldwide. For the first time, humanity wasn't looking at an artist's impression. We were looking at a real photograph of an event horizon's shadow. The object of that photo, M87*, has a mass of about 6.5 billion suns. It's over 1,500 times more massive than our own SGR-A. Its size is just absurd. We need a new way to measure it. So let's use light itself. If you could shine a flashlight across the shadow of M87*, that beam of light would need 2.5 days to get from one side to the other. 2.5 days for the fastest thing in the universe to cross the shadow of a single object. We have journeyed from a black hole the size of a city to one that would engulf our solar system. But we have not yet met the titans. Even these unimaginable monsters are about to be humbled. The climax. The ultimate titans. Everything so far has been a prelude. We are now venturing to the edge of the known universe, to gaze upon objects that redefine the word big. For a long time, the undisputed king was a black hole powering a quasar named TUN 618. A quasar is an extremely bright galactic core, where a supermassive black hole is feeding so ferociously that the light from the process outshines its entire galaxy of billions of stars. The light from TUN 618 began its journey over 10 billion years ago, when the universe was just a toddler. We are looking back in time, at a primordial monster. By measuring the gas swirling around its center, astronomers calculated its mass. The old estimate was a staggering 66 billion solar masses. However, more recent measurements have revised this down to a still unfathomable 40 billion solar masses. Around the same mass is another contender for the heavyweight title. The black hole at the center of the galaxy Holmberg 15A, also clocking in at an estimated 40 billion solar masses. 40 billion suns. That's nearly 10,000 times the mass of our own Sagittarius A. Let's try to picture the size of one of these 40 billion solar mass titans. Our solar system is no longer a useful ruler. It's like trying to measure an ocean with a teaspoon. The event horizon of one of these black holes is so vast, you could line up more than 25 of our solar systems all the way out to Neptune end to end just to cross its radius. And what about light? A beam of light would take over 3 weeks to cross its shadow. These confirmed giants are almost beyond comprehension. But what if there's something even bigger? Enter the challenger, Phoenix A. This black hole sits at the center of the Phoenix cluster, 8.5 billion light-years from Earth. Unlike TUN 618 or Holmberg 15A, its mass hasn't been measured directly. It's an estimate based on models, and there's still debate. But the estimated number is mind-shattering. 100 billion solar masses. 100 billion suns. An object so massive it's approaching the theoretical upper limit for how big a black hole can get before its own energy blasts away its food supply. Its proposed event horizon would be nearly 600 billion kilometers across. That's a distance so vast it would take a beam of light 71 days to circle it. Whether one of the 40 billion solar mass kings or the speculative 100 billion solar mass challenger holds the ultimate title, the conclusion is the same. We have reached the plausible limit of cosmic scale, staring into an abyss that is fundamentally, beautifully, and terrifyingly beyond our human comprehension. Our journey across scale is at an end. We started with our sun, then used our solar system as a ruler, and watched as it was swallowed whole. We used the speed of light itself as a clock and found that even it was too slow. From stellar mass black holes the size of cities, we jumped to our galaxy's heart, Sagittarius A. From there, we visited the gallery of giants, Cygnus A, M87*, and finally, the ultramassive titans like Ton 618 and Holmberg 15A, each weighing 40 billion suns. We even glanced at the hypothetical king, Phoenix A, a monster of 100 billion solar masses that may sit at the very edge of possibility. The scale is overwhelming, but it should also inspire wonder. These objects are the gravitational architects of the universe. They govern how galaxies form and evolve. Their mergers send ripples in spacetime gravitational waves echoing across the cosmos. They are a fundamental part of the cosmic story. And our knowledge is just beginning. Astronomers are now hunting for stupendously large black holes, or slabs, theoretical objects that could be even bigger, lurking invisibly in the dark. How did they get so big, so fast? Is there a hard limit? What secrets are hidden inside their event horizons, where our laws of physics break down? These are the questions driving the next generation of astronomy. We live on a tiny, fragile world, orbiting an average star in a quiet suburb of one galaxy among trillions. At the heart of that galaxy is a monster, and that monster is a lightweight compared to the true titans of the cosmos. And yet, from this tiny world, we can look out. We can measure. We can calculate. And in our own way, we can begin to comprehend the sheer, mind-breaking scale of it all. The universe isn't just bigger than we imagine. It's bigger than we can imagine. And the search for its ultimate secrets has only just begun. Black hole size comparison from smallest to largest. Imagine a monster the size of a city that weighs more than our sun. This isn't science fiction. It's a stellar mass black hole, and it's where our story begins. We're about to go on a cosmic safari, hunting for the biggest, baddest, most mind-bending objects in the entire universe. We'll start with these city-sized ghosts, the leftovers of dead stars, and work our way up, one terrifying step at a time. By comparing these cosmic predators to things we can almost wrap our heads around, we'll build a ladder of scale, climbing higher and higher until we reach the incomprehensible titans that anchor entire galaxies. These are objects so vast they break our language and our imagination, weighing as much as billions of suns. What you're about to see will change the way you look at the night sky forever. The universe isn't empty. It's filled with monsters. So, let's start with a basic question. What even is a black hole? You've probably heard it described as a place where gravity is so strong that nothing, not even light, can escape. And while that's true, it feels a little sterile. It misses the raw reality of what these things are. A better way to think of a black hole is as the universe's most efficient crushing machine. It's a point of infinite density, a singularity hidden behind a one-way door called the event horizon. Cross that threshold, and you are simply removed from the observable universe. You're gone. The size of that door, the diameter of the event horizon, is what we mean when we talk about the size of a black hole. And the smallest of these doors belong to the stellar mass black holes. The runts of the litter. Stellar mass black holes. Our journey begins with the ghosts of giants. When a truly massive star, one born with 20 or more times the mass of our sun, gets to the end of its life, it doesn't go quietly. Its core, now out of nuclear fuel, can't fight against its own crushing weight. In a blink, gravity wins the long war. The core collapses, triggering a spectacular explosion called a supernova that can outshine its entire galaxy for a few weeks. But left behind, at the heart of the fading fire, is the star's crushed core. If this remnant is massive enough, nothing can stop its collapse. It shrinks past the point of being a neutron star, crushing itself down into a single point. A stellar mass black hole is born. These are the most common type, with hundreds of millions likely scattered across our own Milky Way. But common doesn't mean tame. They usually pack the mass of 3 to 50 suns. To put that in perspective, our sun contains 99.8% of all the mass in our solar system. Now, imagine 50 of them, squeezed into a space so small it's hard to even picture. That's the paradox of a black hole. Huge mass in a tiny volume. Let's take one of the smallest contenders ever found, a black hole with a mass of just about 3.6 times our sun. Its event horizon, the point of no return, would be just over 21 kilometers across. You could fit this black hole comfortably inside most major cities. It's an object with the weight of 3 suns, but it's smaller than Manhattan. Think about that density. If you could somehow grab a teaspoon of matter from the singularity at its heart, that single teaspoon would weigh billions of tons more than every car, truck, and ship on Earth combined. This is what we're dealing with. Matter compressed to its absolute limit. But let's put a name to one of these, the first one ever widely accepted by scientists. Cygnus X1. About 7,000 light-years away, Cygnus X1 is a true monster in disguise. We now know it weighs in at a staggering 21.2 times the mass of our Sun. Yet its event horizon is only about 124 kilometers across. You could drive that distance in an hour. And this tiny titan isn't alone. It's locked in a gravitational death dance with a huge blue supergiant star named HDE 226868. This star is a beast in its own right, but its surface is being violently pulled and warped into a teardrop shape by its tiny, invisible partner. It's bleeding a river of superheated gas into space. This gas doesn't fall straight in. It gets caught in the black hole's gravity, forming a swirling, white-hot structure around it called an accretion disk. As this stolen star stuff spirals inward, friction heats it to millions of degrees, causing it to glow fiercely in X-rays. That's how we found Cygnus X1 in the first place. It's one of the brightest X-ray sources in our sky. An object barely wider than a small state is outshining a star thousands of times its size, just by slowly eating it. Stellar mass black holes can grow, but they usually top out at a few dozen solar masses. For a long time, astronomers kept finding these, and then a huge, mysterious gap. There was a desert in the data until you reached the next weight class, which starts at a whopping 100,000 solar masses. Where was everything in between? The missing link. Intermediate mass black holes. This was the puzzle of the intermediate mass black holes, or IMBHs. They're the elusive middle children of the black hole family, ranging from 100 to 100,000 times the Sun's mass. For decades, they were just a theory. It seemed the universe was great at making small black holes from stars and colossal ones in the centers of galaxies, but terrible at the in-between sizes. Why? Well, the recipe was a mystery. A single star just isn't big enough to collapse into an IMBH. And the special conditions at the heart of big galaxies, where the supermassive ones are born, are hard to replicate. The leading ideas suggest a couple of paths. One is a runaway merger in a dense, young star cluster, where multiple massive stars could collide to form one ultra-massive star that then collapses. Another is that smaller, stellar mass black holes could merge over and over, gradually building a bigger one. For years, the evidence was shaky. We'd find hints, like X-ray sources that were too bright to be a single stellar black hole but not in the center of a galaxy. But solid proof was hard to find. That is, until the gravitational wave detectors LIGO and Virgo came online. In 2020, they detected the collision of two black holes which created something new. The result of their merger was a single black hole with a mass of about 142 suns, the first definitive, slam-dunk observation of an IMBH being born. Since then, we've gotten better at hunting them. One clever way is to look for a specific kind of explosion. A white dwarf, the dense remnant of a sun-like star, is so compact that it can only be ripped apart, what we call a tidal disruption, by the gravity of an IMBH. A smaller black hole isn't strong enough, and a supermassive one is so big it would swallow the white dwarf whole before it could be shredded. Finding the specific flare from a white dwarf being torn to shreds is a smoking gun for an IMBH, and astronomers are actively hunting for these events. These discoveries are thrilling because they bridge the gap between the small and the truly enormous. IMBHs are likely the seeds from which their larger cousins grow. Finding them is like finding the missing link in the evolutionary chain of cosmic monsters, showing us how the universe scales up its creations. And believe me, the jump in scale from here is not a step, it's a leap straight into the abyss. The galactic anchors. Supermassive black holes. Now we enter the domain of the true titans. At the heart of almost every large galaxy, including our own Milky Way, there lurks a supermassive black hole. These aren't just objects in a galaxy. They are a fundamental part of it, the gravitational anchors for trillions of stars. Our first stop is right here in our cosmic backyard, 27,000 light-years away at the center of the Milky Way. Here resides Sagittarius A*, our very own supermassive black hole. For decades, astronomers watched stars whipping around an invisible point, with one star, S2, hitting speeds of 2.5% the speed of light. By mapping those orbits, they calculated the mass of the object they were circling. Just over 4 million times the mass of our Sun. 4 million suns. All of that mass is squeezed into a region so small it's hard to imagine. We now have a picture of it, thanks to the Event Horizon Telescope. It shows a glowing ring of gas around a central darkness, the black hole's shadow. The diameter of this shadow is about 52 million kilometers. That sounds huge, until you realize the orbit of Mercury is more than twice as wide. The shadow of our galaxy's central monster would fit comfortably inside the orbit of the innermost planet. And for all its power, Sagittarius A is considered a fairly modest, even meager, supermassive black hole. Others make ours look like a pebble. Let's travel 55 million light-years to the heart of the colossal galaxy Messier 87. M87 is a true giant, and at its core lies a black hole to match. M87*, the very first black hole ever directly imaged. The picture looks eerily similar to our own black holes, but the scale is completely different. M87* has a mass of 6.5 billion solar masses. That's over 1/500 times more massive than Sagittarius A. Let's try to picture that. The event horizon of M87 is about 38 billion kilometers across. Our entire solar system, out to Pluto's orbit, is roughly 12 billion kilometers wide. You could fit our whole solar system inside the event horizon of M87*, 3 times over. If you replaced our Sun with M87*, its edge would stretch far beyond every planet. We'd already be inside the belly of the beast. And this monster is active, famously shooting a jet of plasma out into space that stretches for 5,000 light-years. This is no longer a monster the size of a city. This is a monster the size of a solar system. The ultramassive behemoths. We've seen black holes that can swallow stars, and black holes that can swallow solar systems. But the universe isn't done with us. We are now entering a new category so extreme they needed a new name. Ultramassive black holes. These are the apex predators of the cosmos, weighing more than 10 billion suns. They live in the centers of the biggest galaxies in the universe, which are themselves the kings of vast galaxy clusters. The swirling vortex of matter being fed into them, their accretion disk, can shine brighter than their entire host galaxy. We call that a quasar, and some are so bright we can see them from across the observable universe. Let's start with the black hole at the heart of Holmberg 15A, a supergiant galaxy 700 million light-years away. By tracking the stars in its core, astronomers found a record breaker: 40 billion solar masses. 40 billion. That's nearly 10,000 times the mass of our own Sagittarius A. Its event horizon would be about 236 billion kilometers across. You could line up nearly 20 of our solar systems, side by side, and they would all fit inside this single object. The Voyager 1 spacecraft, which has been traveling away from Earth for nearly 50 years, is just over 24 billion kilometers away. It would have barely scratched the surface of this thing. What's crazier is that it's actually too big for its galaxy, suggesting a violent past of devouring other supermassive black holes. And yet, Home 15A is not the king. For that, we must travel to a quasar so distant we're seeing it as it was over 10 billion years ago. Its name is TUN 618. We see it as a blazing accretion disk shining with the light of 140 trillion suns, one of the most luminous objects in the known universe. To power that light show, the engine at its heart has to be almost beyond belief. The widely cited estimate for its mass is 66 billion solar masses. 66 billion. The number is almost meaningless. It's over 15,000 times more massive than Sagittarius A. Its event horizon is about 390 billion kilometers across. You could line up our solar system over 40 times from one end of this object to the other. Light itself, the fastest thing there is, would take more than 2 weeks to cross its diameter. This object isn't just part of a galaxy. For all practical purposes, it is the galaxy, a single object that outshines thousands of galaxies filled with trillions of stars. We might be looking at the largest single coherent object in the universe. We've journeyed from a black hole smaller than a city to an object that can swallow dozens of solar systems at once. If this journey through the most extreme objects in existence has expanded your view of the cosmos and left you in awe, consider subscribing. There are so many more mysteries to explore, and we're just getting started. And yet, the story might not even end there. We've always wondered, is there a limit? How big can a black hole get? Some theories proposed an upper limit of around 50 billion solar masses, a point where the black hole's food source would become unstable and form stars instead of feeding the monster. TUN 618 already pushes that limit to its breaking point. But the universe often has other ideas. There are candidates that could be even bigger. Deep in a galaxy cluster 5 billion light-years away sits an object called Phoenix A. Its mass hasn't been measured directly with the same precision, but estimates place it at a mind-shattering 100 billion solar masses. 100 billion suns. An event horizon spanning 590 billion kilometers, roughly 100 times the distance from the Sun to Pluto. If those numbers hold, Phoenix A wouldn't just break the theoretical limit, it would shatter it. From a monster the size of a city to a cosmic horror that could consume entire galaxies. This is the staggering range of black holes. They are the ashes of dead stars and the anchors of living galaxies. They are where our laws of physics break down, and yet they power the brightest lights we can see. They are a constant, humbling reminder that no matter how much we learn, the universe will always be bigger, stranger, and more magnificent than we can possibly imagine. So when you look up at the night sky, at all those points of light, remember the darkness in between. For it is in that darkness that the true giants dwell. The invisible giant hiding in every galaxy. At the heart of nearly every large galaxy, including our own Milky Way, most scientists are certain an invisible monster is hiding. It has the mass of 4 million suns, yet the object itself is a perfect void. So, if we can't see it, how do we know it's there? The answer lies in a cosmic crime scene, where entire stars are being thrown around at incredible speeds, orbiting a phantom that has been pulling the strings of our galaxy for billions of years. This is a detective story, a quest to uncover the strange evidence and frantic star movements that prove this invisible giant exists. Our universe is filled with objects of unimaginable scale and power. We're talking stars bigger than our solar system and nebulae stretching for hundreds of light years. But what if the most influential object in our galactic home, the true titan that dictates the fate of 100 billion stars, was something we couldn't see at all? Something with a gravitational grip so absolute that not even light can escape it. For decades, this was a tantalizing, almost maddening puzzle for astronomers. They could feel its presence. They could see the chaos it created. But the culprit remained stubbornly in the shadows, a ghost in the machine of the Milky Way. This isn't just a story about a strange object. It's a story about human ingenuity, about our relentless drive to see the unseeable. It's a multi-generational cosmic detective story, piecing together clues to hunt down a monster. And what we found at the end of that hunt would not only change our understanding of our own galaxy, but of every large galaxy in the cosmos. The mystery. A disturbance at the heart of the galaxy. Our story begins not with a bang, but with a hiss. In the early 1930s, a young radio engineer named Karl Jansky was tasked by Bell Telephone Laboratories with a simple job: find the sources of static that could interfere with transatlantic radio calls. He built a massive, rotating antenna in a New Jersey field, a contraption the locals called Jansky's merry-go-round. For months, Jansky patiently listened. He identified the obvious culprits: distant thunderstorms and local interference. But one sound was different. A faint, steady hiss that rose and fell on a precise 23-hour and 56-minute cycle. That's not the 24-hour cycle of our sun. It's a sidereal day, the time it takes the Earth to rotate relative to the distant stars. This was a crucial clue. The source wasn't from Earth or even our solar system. It was coming from deep space. Jansky mapped the signal and pinpointed its origin: a specific spot in the constellation of Sagittarius. Astronomers knew this was the direction of the Milky Way's center, but his discovery was met with more curiosity than excitement. The field of radio astronomy didn't even exist yet. Jansky had just invented it by accident. He'd opened a new window to the universe, but for years, no one was quite sure what to look for. Decades passed. After World War II, scientists with new, more powerful radio telescopes began to systematically scan the heavens. In 1974, astronomers Bruce Ballack and Robert L. Brown used the Green Bank Observatory's interferometer to look again at that strange spot. They found something astonishing. Right at the presumed galactic center was an incredibly bright, yet remarkably compact, radio source. They named it Sagittarius A. But a name was just a label. The mystery of what it was had only deepened. Here was the puzzle, the start of our cosmic crime scene. Whatever was producing this intense radio energy was completely invisible to optical telescopes. The galactic center is a chaotic, violent place, shrouded in thick clouds of interstellar dust and gas that block visible light. Imagine trying to see a candle flame in a continent-sized dust storm. That's the challenge astronomers faced. Yet, through this veil, the radio hiss that Jansky first detected poured out, signaling something immensely powerful. What could be so energetic, yet so small and dark? Scientists had theories. Maybe it was a dense cluster of young, hot stars. Or perhaps a swarm of exotic remnants like neutron stars or smaller black holes. But these ideas had problems. A star cluster that big should be visible in other ways. And Sagittarius A* seemed to be a single, point-like object. The evidence was contradictory. It was like finding a scorch mark the size of a city block but no bomb, no wreckage, no residue. There was only a single, infinitesimally small point where all the energy seemed to come from. The clues didn't add up. The galactic core was hiding a secret, and to solve it, astronomers needed to become detectives. They needed to find a witness. The investigation. The hunt for the unseen suspect. By the 1990s, the mystery of Sagittarius A* was one of the hottest puzzles in astrophysics. The case had gone cold, not for lack of interest, but for lack of technology. The dust clouds of the Milky Way were just too thick. This challenge required a new generation of investigators and new forensic tools. Enter our two competing detective teams. In Germany, a team led by Reinhard Genzel at the Max Planck Institute was using the European Southern Observatory's telescopes in Chile. In the United States, Andrea Gheza's team at UCLA was using the mighty W.M. Keck Observatory in Hawaii. Both teams knew they had to abandon visible light. Their secret weapon was infrared astronomy. Infrared light has a longer wavelength that lets it pass through the dense dust, like cosmic night vision goggles. If there were stars orbiting the mystery source, infrared telescopes could, in theory, spot them. But seeing in infrared wasn't enough. Earth's atmosphere creates a shimmer that blurs the light from distant stars, like trying to read a newspaper at the bottom of a swimming pool. The subtle movements of stars 26,000 light-years away would be completely smeared out. This is where the real genius comes in. Both teams pioneered a revolutionary technology called adaptive optics. It's a stunning feat of engineering. A sensor constantly measures atmospheric distortion using a guide star, and a computer uses the data to control a deformable mirror. This mirror flexes hundreds of times per second to counteract the blurring. It's like giving the telescope a perfect, constantly updating pair of glasses. The results were miraculous. Suddenly, the blurry blob at the galaxy's center resolved into a swarm of sharp, individual points of light. They could see the stars. Now, the real detective work could begin. The plan was simple in concept, monumental in execution. Take pictures of the same patch of sky, year after year, and meticulously track the stars closest to Sagittarius A. If a massive object was there, its gravity would be yanking these stars around in observable orbits. Just as we can calculate the sun's mass by observing the planets, they hoped to weigh this unseen object by tracking its stars. This was not a quest for the impatient. It was a slow, painstaking process of collecting data, one observation at a time, for decades. Each new data point was a clue. A star moving a few milliarc seconds here, another accelerating there. Genzel's team at the Very Large Telescope, VLT, and Gheza's team at Keck were in a friendly but fierce competition. Each new paper spurred the other to push their technology harder, providing the independent confirmation that is the bedrock of science. The world watched as they slowly built their case. They were mapping the scene of the crime, and soon, they would find a star witness whose testimony would be undeniable. The evidence. The star that sealed the deal. After years of patient observation, the data began to paint an astonishing picture. The stars at the very center of the Milky Way weren't just drifting. They were swarming like angry bees around a single, unseen point. The exact location of Sagittarius A. This wasn't the calm, stately motion of stars in our neighborhood. This was a cosmic mosh pit, a place where gravity was turned up to 11. Out of this stellar swarm, one star emerged as the key witness. Gheza's team called it S02, while Genzel's team called it S2. Its orbit was a relatively short 16 years, meaning they could track its full journey. And what a journey it was! As S2 neared the central point, its speed became breathtaking, accelerating to over 650 kilometers per second, almost 3% of the speed of light. At that speed, you could get from London to New York in under a second. The star was being whipped around by a gravitational force of unimaginable intensity. Then, after swinging past its closest point, it would be flung back out, slowing as it climbed away from the gravitational well, only to fall back in again, year after year, in a perfect elliptical orbit. This was the smoking gun. Using Kepler's laws of motion, the same physics that describe how planets orbit the Sun, the scientists could now perform a simple but profound calculation. To keep a star like S2 locked in such a tight, fast orbit, the object it was orbiting had to be spectacularly massive. Both teams, working independently, crunched the numbers. The answer was staggering. The object at the center of our galaxy has a mass of about 4 million times that of our Sun. But mass was only half the equation. The object's size was just as important. At its closest approach, S2 swings by the central mass at a distance of only about 17 light-hours. That means all 4 million solar masses must be crammed into a region of space smaller than our solar system. This is where all other explanations fell apart. A cluster of 4 million stars? No, it would be incredibly bright or the stars would have already collided. A swarm of smaller black holes or neutron stars? No, they would have flung each other out of the cluster long ago. A weird clump of exotic matter? Nothing known could clump so densely and produce the observed radio waves. The detectives had cornered their suspect. Its mass, 4 million suns. Its size, confined to a space so small it could fit neatly inside our solar system. Its defining characteristic, it was completely, utterly dark. There is only one object in the universe that fits this description. The evidence was so overwhelming it pointed to one conclusion. The invisible giant at the heart of the Milky Way had to be a supermassive black hole. The revelation. The monster in focus. The conclusion was inescapable, a verdict delivered by the laws of physics. The decades-long hunt that began with a faint radio hiss had led to one suspect. Sagittarius A*, as it came to be known, was a supermassive black hole. This wasn't just a theory anymore. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy, an achievement they shared with Roger Penrose for his theoretical work on black holes. But even with a Nobel, the ultimate proof is a picture. And how do you photograph an object that traps light? The answer came from an audacious project. The Event Horizon Telescope, or EHT. The EHT is not a single telescope but a global network of radio observatories, synchronized to create a virtual telescope the size of Earth itself. This planetary-scale observatory had the power to see a donut on the surface of the Moon, and it was just powerful enough to attempt the impossible: to take a picture of a black hole's shadow. A black hole's shadow is the silhouette it casts against the hot, glowing matter swirling around it. As gas and dust form a superheated accretion disk, the event horizon, the point of no return, should appear as a dark void. In 2019, the EHT collaboration released a picture that stunned the world: the supermassive black hole at the heart of the M87 galaxy. There it was. A fiery ring of light surrounding a perfect circle of blackness. Humanity had seen the unseeable. The team then turned their planet-sized eye to our own galactic center. Sagittarius A* was a much harder target, smaller and more turbulent. In May 2022, they succeeded. They released the first ever image of Sagittarius A. There it was. A familiar ring of light with a dark shadow, confirming its mass and size. The monster was real. Now, while the black hole itself is dark, we've recently learned its neighborhood hasn't always been so quiet. Data from the XRISM X-ray telescope shows evidence that our sleeping giant likely had a massive flare-up within the last 1,000 years, briefly erupting with incredible power. Is the case completely closed? In science, it rarely is. A fascinating alternative theory suggests the object isn't a black hole at all, but a bizarre, ultra-dense clump of fermionic dark matter. Proponents argue this could mimic a black hole's gravity, star-flinging orbits, and even the shadow seen by the EHT. It's a mind-bending idea, and while the supermassive black hole remains the prime suspect by a long shot, it's a great reminder that the universe can always have another surprise up its sleeve. The implications. A universe of giants. Confirming Sagittarius A** did more than just solve a local mystery. It revealed a fundamental truth about the cosmos. Astronomers realized the Milky Way isn't special. By looking at other galaxies, they found the same telltale signs. Stars orbiting unseen centers at impossible speeds. The conclusion was profound. Nearly every large galaxy hosts a supermassive black hole at its core. Our invisible giant isn't an anomaly, it's the norm. We live in a universe of giants. And our 4 million solar mass black hole is pretty modest. The black hole in M87, the first one imaged, weighs over 5 billion solar masses. Even that pales in comparison to the true titans, like the one powering the quasar Ton 618. Located over 10 billion light-years away, it tips the scales at an almost incomprehensible 66 billion times the mass of our Sun. Its event horizon is so vast that light would take a week to cross it. If you placed it in our solar system, it would swallow every planet and extend into a void larger than 40 solar systems laid end to end. This has led to one of the biggest questions in cosmology. Which came first, the galaxy or the black hole? We used to assume galaxies formed first, with matter sinking to the center. But recent discoveries, especially from the James Webb Space Telescope, are flipping that idea on its head. In the very early universe, we see black holes that seem far too large for their young, small galaxies. This has given rise to the direct collapse theory. In this scenario, the black hole comes first, acting as a gravitational seed around which the galaxy then forms. They aren't just residents, they're the architects. These cosmic anchors are also active engines. As matter falls in, some is blasted back out in colossal jets of energy. These jets can blow away gas, quenching star formation across the galaxy. Conversely, they can also compress gas clouds elsewhere, triggering bursts of star birth. The supermassive black hole acts as a galactic thermostat, regulating the life and death of stars on a cosmic scale. From the quiet giant in our own backyard to raging quasars that outshine a trillion suns, supermassive black holes are not just a curiosity. They are a fundamental component of the universe, the invisible scaffolding upon which the cosmos is built. From a faint hiss in a field in New Jersey to a planet-sized telescope staring into the abyss, the journey to find Sagittarius A is a testament to scientific discovery. We followed the clues. Strange radio whispers from the heart of the Milky Way, the frantic dance of a star being flung through space by an unseen partner, and finally, a shadow cast against a ring of fire. Through decades of patient observation and brilliant innovation, we solved the mystery. We proved that at the very center of our galactic home sits a monster. A supermassive black hole, 4 million times the mass of our Sun, now confirmed and photographed. And in doing so, we revealed that these invisible giants are the gravitational anchors of almost every galaxy, the hidden rulers of the cosmos. The story of Sagittarius A is a cosmic detective story, but it's also our story. It shows that even the most profound secrets of the universe are not beyond our reach. The monster at the heart of our galaxy has been unmasked, but the awe it inspires, and the new questions it raises, will fuel our journey into the cosmos for generations to come. If you enjoyed this journey to the heart of our galaxy, consider subscribing for more deep dives into the mysteries of our universe. Our galaxy's black hole is weirder than you think. For as long as we've looked at the stars, we've told stories about the heart of our galaxy, the Milky Way. Ancient cultures saw a celestial river, the spine of night, or a pathway for the gods. But for most of modern history, what was really at the galactic center was a profound mystery. It's about 27,000 light-years away, a frankly impossible distance, cloaked behind an impenetrable veil of cosmic dust and gas. Our most powerful optical telescopes couldn't see a thing. But astronomers are detectives of the highest order. They knew something big was there. Not just a dense bunch of stars, but something else entirely. A gravitational monster, a silent puppet master about 3 million times more massive than our Sun, pulling the strings on the frantic, high-speed dance of the stars closest to it. We now have a picture of this beast. We even have a name. Sagittarius A. And the more we learn about the giant in our own cosmic backyard, the more we realize it's far weirder, far more complex, and way more fascinating than we ever dared to imagine. This is the story of that beast. It's a story of a decades-long hunt for an invisible phantom, a tale of scientific ingenuity pushing the limits of what's possible, and the revelation of a cosmic monster that is both quieter and stranger than fiction. The cosmic mystery. A hidden heart. Imagine you're trying to see a single candle flame in the middle of a sprawling, fog-drenched metropolis from thousands of miles away. Now, imagine that city is also choked with billowing clouds of smoke, obscuring your view at every turn. That's pretty much the challenge astronomers faced when trying to peer into the heart of the Milky Way. Our galaxy is a vast, flat disk, about 100,000 light-years across. We live out in one of its spiral arms, roughly 2/3 of the way from the center. From our vantage point, looking toward the galactic core means looking through tens of thousands of light-years of, well, stuff. Billions of stars, sure. But also colossal clouds of interstellar gas and dust. This isn't the kind of dust under your bed. It's made of tiny grains of carbon, silicates, and other elements forged in the hearts of long-dead stars. While these grains are minuscule, over cosmic distances, they form an impenetrable shroud. This shroud is what's known as the zone of avoidance. Early astronomers mapping the sky noticed a band where they just couldn't see any other galaxies. It wasn't that galaxies weren't there. It was our own galaxy's dust blocking the view, like looking through a dirty window. This same dust makes it impossible to see the Milky Way's core in visible light. The light from the stars there is scattered and absorbed long before it can ever reach our telescopes. For decades, this left the core as a place of pure theory. Scientists knew from the laws of gravity that the galaxy had to have a massive central point that everything orbits, just like the planets orbit the sun. The rotation of hundreds of billions of stars implied a massive gravitational anchor. But what was it? Was it just a super-dense cluster of millions of stars, packed so tightly their collective gravity held the galaxy together? Or was it something more exotic? The clues were tantalizing. The orbits of the stars we could see near the center suggested they were moving at incredible speeds way faster than could be explained by the visible matter alone. Something unseen, something incredibly massive yet astonishingly compact, had to be hiding behind that veil. The mystery wasn't just what was at the center, but how we could possibly see it. To solve this, astronomers needed a new way of looking at the universe. They needed a light that could pierce the fog. The hunt begins. Echoes in the dark. The first crack in the cosmic veil didn't come from a telescope that saw light, but from one that heard the universe's whispers. The story of Sagittarius A**'s discovery begins not with a flash, but with static. In the early 1930s, a young physicist named Karl Jansky, working for Bell Telephone Laboratories, was tasked with tracking down sources of static that could interfere with transatlantic radio calls. He built a bizarre-looking antenna, a rotating mess of brass pipes and wood that looked more like modern art. They called it Jansky's merry-go-round. As he listened to the hiss of the cosmos, he found the usual suspects: nearby and distant thunderstorms. But he also found something else. A faint, steady hiss he couldn't explain. Patiently, he tracked this signal for months. He noticed that it peaked not every 24 hours, but every 23 hours and 56 minutes, the exact time it takes for the Earth to rotate relative to the distant stars, not the Sun. This was the crucial clue. The source wasn't on Earth, or even in our solar system. It was coming from deep space. He traced it to a specific spot in the sky, the constellation of Sagittarius, right in the direction of the Milky Way's center. Karl Jansky had detected the first radio waves from the heart of our galaxy. He had opened a new window onto the universe. For decades, his discovery was mostly a curiosity. Radio astronomy was just getting started. But after World War II, fueled by advances in radar tech, the field exploded. Astronomers started building massive radio dishes, pointing giant metal ears to the heavens to map the sky in frequencies our eyes can't see. Radio waves, with their long wavelengths, can pass through those cosmic dust clouds almost completely unbothered. Where visible light is stopped cold, radio waves sail right on through. By the 1950s and 60s, radio astronomers had created detailed maps of the galactic center, revealing a complex and energetic region. And right at the heart of it all, at the galaxy's gravitational bullseye, was an intensely bright and incredibly compact radio source. In 1974, two astronomers, Bruce Ballack and Robert L. Brown, used the powerful green bank interferometer to pinpoint this source with stunning accuracy. They saw it was extraordinarily bright, yet remarkably small. To mark how special it was, they gave it a name. Following the conventions of the time, they called it Sagittarius A, for the brightest radio source in the Sagittarius region. But they added an asterisk, a symbol from atomic physics used to denote an excited state. This wasn't just any radio source. It was energetic. It was Sagittarius A. The hunt was on. They had found the X that marked the spot. The source was compact, powerful, and sat exactly where the galaxy's gravitational center should be. But a bright radio signal wasn't proof of a black hole. It could still be a dense star cluster or some other exotic object. To prove what Sagittarius A** really was, astronomers needed more than a single point of light. They needed to see its influence. They had to catch it in the act of commanding the cosmos. The star dancers, smoking gun evidence. The proof didn't come from seeing Sagittarius A** itself, but from watching what it did to its neighbors. For decades, astronomers pointed not just radio telescopes, but powerful infrared telescopes toward the galactic center. Infrared light, like radio waves, can also punch through the dust clouds much better than visible light, letting scientists see the individual stars swarming around the core. And what they saw was breathtaking. The center of our galaxy is one of the most extreme environments you can imagine. Stars there are packed 1,000,000 times more densely than in our own solar neighborhood. And at the very heart of this stellar swarm, a handful of stars were behaving very, very strangely. They were moving at absolutely mind-boggling speeds, whipping through space like celestial bullets. Two teams of astronomers, one led by Reinhard Genzel and the other by Andrea Ghez, began one of the longest and most painstaking observational campaigns in astronomy's history. Starting in the 1990s, they used the world's most advanced infrared telescopes to track the movements of these central stars, year after year, with meticulous precision. They zeroed in on one star in particular, named S2. Over the course of their study, they watched S2 complete an entire orbit. Its path was a perfect ellipse, just as Kepler's laws would predict for an object orbiting a single, central mass. But the scale was almost beyond comprehension. S2 was tracing a path around something completely invisible, and its speed was staggering. At its closest approach, S2 screamed past the invisible center at over 17 million miles per hour, about 2.5% of the speed of light. It gets as close as 11 billion miles before being flung back out on its 16-year journey. This was the smoking gun. Using the precise shape and period of S2's orbit, the teams could calculate the mass of the object it was orbiting. The math was inescapable. To keep a star like S2 on such a tight leash, to whip it around with that much gravitational force, the central object had to contain the mass of about 4 million suns. And all of that mass had to be crammed into a space smaller than the orbit of our solar system's planets. So, what could it be? A cluster of 4 million stars? No. Packed that tightly, they would have either collided and merged or flung each other out of the system in a cosmic blink. A collection of smaller black holes or neutron stars? Again, no. Such a cluster wouldn't be stable and couldn't create the single, neat gravitational point that S2 was so clearly orbiting. There was only one object that fit the description. A single, supermassive black hole. The decades of patient observation, tracking the ghost-like dance of a single star some 27,000 light-years away, had provided the definitive evidence. For their monumental work confirming this supermassive compact object, Reinhard Genzel and Andrea Ghez were awarded the 2020 Nobel Prize in Physics. They had proven that the monster in the dark was real. But what exactly is this monster? What is this monster? Black hole 101. So, we have a monster. A creature with the mass of about 4.3 million suns, to be precise, lurking in the shadows. But calling it a monster is both perfectly fitting and a little misleading. To understand Sagittarius A*, we need to peel back the layers of sci-fi cliché and look at what a black hole, and specifically a supermassive black hole, really is. First off, a black hole is not a cosmic vacuum cleaner. It doesn't roam the galaxy, sucking up everything in its path. A black hole is simply an object with so much mass packed into such a tiny space that its gravitational pull becomes inescapable. It's the natural end for the most massive stars. When a star many times bigger than our Sun dies, it collapses under its own immense gravity, crushing down into an infinitesimally small point of infinite density, a singularity. Surrounding this singularity is a boundary, a one-way door, known as the event horizon. This isn't a physical surface. It's simply the point of no return. Anything that crosses it, a star, a planet, even a beam of light, can never escape. Gravity is just too strong. This is why black holes are black. They trap all light that falls in. The size of a black hole is defined by its event horizon, or its Schwarzschild radius. For a regular, stellar mass black hole, this might only be a few miles across. But Sagittarius A isn't a regular black hole. It's a supermassive black hole. These are a completely different class of object, millions to billions of times the mass of our Sun. They aren't formed from a single star's death. Their origin is one of the great unsolved mysteries of cosmology. They likely grew over billions of years, either by gobbling up countless stars and smaller black holes or from the direct collapse of enormous gas clouds in the early universe. And despite its colossal mass, the event horizon of Sagittarius A is, cosmically speaking, surprisingly small. It has a diameter of about 14.6 million miles. That sounds huge, but it's actually smaller than Mercury's orbit around our Sun. Imagine squishing 4 3 million suns into a ball so small it would fit comfortably inside the path of our solar system's innermost planet. The result is an object of almost unimaginable density and gravitational power. This is the creature Genzel and Ghez proved exists. An object that warps the very fabric of spacetime around it. As Einstein taught us, gravity is just the curvature of spacetime caused by mass. A star bends spacetime a little, like a bowling ball on a trampoline. A black hole like Sagittarius A* bends it so severely it creates a bottomless pit, a gravitational well from which nothing can climb out once it falls in. But even this doesn't fully capture its weirdness. It was one thing to prove its existence through the dance of nearby stars. It was another thing entirely to try and take its picture. And that challenge would reveal that our local monster was far from a simple, static object. Sizing up the beast. A tale of two black holes. To really grasp the weirdness of Sagittarius A*, it helps to have something to compare it to. And in the black hole world, one celebrity stands out: M87. In 2019, the world was stunned when the Event Horizon Telescope, EHT, collaboration released the first ever image of a black hole. But it wasn't ours. It was the supermassive black hole in the galaxy Messier 87, a giant elliptical galaxy 55 million light-years away. M87 is a true titan. It weighs in at a staggering 6.5 billion solar masses. It's over 1,500 times more massive than our own Sagittarius A. So a natural question comes up. Why did we image the much more distant and gargantuan M87* first? If SGRA is in our backyard, shouldn't it have been the easier target? The answer is the first major clue to our black hole's strange personality. It comes down to scale and time. The superheated gas and dust swirling around a black hole in what's called an accretion disk orbits at incredible speeds. For the colossal M87*, this material takes days to weeks to complete one orbit. It's like watching a giant, slow-moving carousel. But for the much smaller Sagittarius A*, the gas in its disk whips around in a matter of minutes. Think about trying to take a photograph. M87* was like taking a picture of a mountain. It's huge, and it's not going anywhere fast. You can use a long exposure to gather light and get a clear, stable image. Sagittarius A*, on the other hand, was like trying to take a sharp picture of a hummingbird's wings in a dark room. The subject is changing constantly. The glowing gas the EHT needed to see was swirling and flaring, brightening and dimming, on a timescale of minutes. This rapid variability made imaging SGRA* an immense technical challenge. While M87* was a steady target, SGRA* was a flickering, chaotic dance. The team couldn't just take one long exposure. The image would be a total blur. They had to use incredibly sophisticated new methods, taking countless snapshots and using powerful computer algorithms to piece together a coherent picture from the chaos. They were trying to photograph a ghost that refused to stand still. And this highlights another weird aspect. As colossal as Sagittarius A is, it's actually pretty average, maybe even on the small side, for a supermassive black hole in a spiral galaxy like ours. It's utterly dwarfed by cosmic behemoths like the one powering the quasar Ton 618, which has a mind-shattering mass of 66 billion suns. Next to that, our 4.3 million solar mass black hole is a mere pebble. So we have this relatively small, hyperactive black hole. A temperamental, flickering beast that presented one of the greatest challenges in modern astronomy. The hunt to prove it existed was over. Now, the quest to finally see it was about to reach its climax. The picture we waited for, the Event Horizon Telescope. Taking a picture of Sagittarius A is, to put it mildly, an impossible task. Not just because it's far away and shrouded in dust, but because its very nature is to be invisible. So, how do you photograph something that absorbs all light? You don't. You photograph its shadow. As Einstein's general relativity predicts, the immense gravity of a black hole bends light around it. Light from the glowing, superheated gas orbiting behind the black hole is warped and magnified, creating a bright ring of light that appears to circle a dark central region. This dark patch is the black hole's shadow, the visual imprint of its event horizon against the glowing backdrop. The goal of the Event Horizon Telescope was to capture an image of this very shadow. The problem was resolution. To see something as small in the sky as SGRA*'''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''has the apparent size of a shadow which, despite its huge physical size, on the surface of the Moon you'd need a telescope the size of the Earth itself. Since building a single dish that large is obviously impossible, the EHT collaboration came up with an ingenious solution. They created a virtual telescope of that size. Using a technique called Very Long Baseline Interferometry, VLBI, they linked together 8 powerful radio observatories across the globe, from the mountains of Hawaii to the deserts of Chile, from Spain to the South Pole. By synchronizing these telescopes with incredibly precise atomic clocks and recording their data at the exact same time, they could function as small pieces of a single, planet-sized mirror. In April 2017, this global array of telescopes stared at the heart of the Milky Way for several nights, collecting petabytes of data, so much data, it was too large to send over the internet. Instead, hard drives from each observatory were physically flown to processing centers to be combined and analyzed. Then came the hard part. For 5 years, a team of over 300 researchers from 80 institutes worked to unscramble the data. They had to account for Earth's rotation, atmospheric distortions at each site, and most difficult of all, the frantic, flickering dance of the gas around SGRA. The team developed new algorithms and split into independent groups to reconstruct the image, ensuring the result was real and not just an artifact. Finally, on May 12, 2022, the world saw it. The image was a little blurry, but unmistakable. A glowing, donut-shaped ring of superheated plasma, with a dark, circular void at its center. The shadow of Sagittarius A. It was a stunning confirmation of Einstein's theories. The size and shape of the ring perfectly matched the predictions of general relativity for a black hole of its mass. The bright ring itself wasn't uniform. It had brighter, hot spots, believed to be clumps of gas orbiting close to the event horizon at a staggering 30% of the speed of light. As this material moves toward us, relativistic effects make it appear brighter, and as it moves away, it dims. This is what causes the rapid flickering. The dark center was the abyss itself, the visual evidence of the point of no return. They had done it. They had taken a picture of the void. And in doing so, they unlocked new questions that confirmed our galaxy's black hole is far weirder than anyone thought. The weird part. A quiet giant with a violent past. The image was a triumph, but it also deepened the mystery. It provided the final, irrefutable proof, but also painted the picture of a cosmic oddball. So, what exactly makes Sagittarius A* so weird? First, and most striking, is just how quiet it is. Supermassive black holes are often the engines of their galaxies. In many other galaxies, the central black hole is a raging inferno called an active galactic nucleus, or AGN. These can be the most luminous objects in the universe. As they furiously consume gas and dust, their accretion disks can outshine their entire host galaxy. Sagittarius A is not like that. It's practically starving. Astronomers have famously compared its diet to a person eating a single grain of rice every million years. For a monster of its mass, this level of calm is deeply strange. This brings us to the second weirdness. evidence of a violent past and a flickering present. While it's quiet now, it hasn't always been. Observations from X-ray telescopes have revealed echoes of massive outbursts. Just a couple of hundred years ago, SGRA* was likely thousands, if not millions of times brighter than it is today, suggesting it had a major feast. And even now, it has tantrums. In 2019, astronomers were stunned when SGRA* suddenly became 75 times brighter than usual for a few hours, suggesting it had swallowed a clump of gas. This mix of deep slumber and sudden, violent flashes makes it a far more complex and unpredictable object than a steadily feeding black hole. The third, and perhaps most bizarre, weirdness is its orientation. Some recent, highly advanced analyses of the EHT data suggest something truly shocking. Sagittarius A* might be spinning at incredible speed, with its axis of rotation, the pole from which a jet would be launched, pointed almost directly at Earth. For years, astronomers have seen hints of a weak, sputtering jet, and if this alignment is correct, it means we might have a very special vantage point, looking straight down the barrel. Now, this isn't cause for alarm. The jet is weak and we are 27,000 light-years away. But this alignment is incredibly fortuitous for science. Why it's tilted this way is another mystery. Normally, you'd expect a black hole's spin to be perpendicular to the galaxy's disk, but ours seems to be lying on its side, possibly after a violent merger in its distant past knocked its axis askew. Finally, there's the mystery of the G objects. In the last couple of decades, astronomers have found a handful of bizarre, dusty objects orbiting extremely close to SGRA. They look like gas clouds, but they behave like stars. When one of them, G2, made its closest approach, scientists expected it to be torn to shreds, but it held itself together, stretching out before becoming compact again. The leading theory is that these aren't simple gas clouds, but are likely dust-enshrouded stars, perhaps even bloated stars formed from the merger of a binary pair, a process driven by the black hole's immense gravity. They are a class of object never seen anywhere else, a unique product of our galaxy's extreme heart. A quiet eater with a violent past, a flickering nature, a spin axis that might be pointed right at us, and a collection of strange, puffy star things orbiting it. Our galaxy's black hole isn't just a simple gravitational anchor. It's a complex, dynamic, and deeply weird individual. Our place in the dance. Are we safe? Learning there's a 4 million solar mass monster at the center of our galaxy, one that might even be pointing a jet in our general direction, naturally leads to a very personal question. Are we in any danger? The answer, in short, is a resounding no. We are perfectly safe. The first reason is simple: distance. The latest measurements place us about 25,800 light-years away from Sagittarius A. That is an immense cosmic gulf, about 152 quadrillion miles, if you're counting. Even if SGRA* were to fire up its jet to full power like a raging quasar, its effects would be vastly diluted over that enormous distance. We are far, far outside any conceivable danger zone. The second reason is our orbit. Our Sun and the entire solar system are in a stable, predictable orbit around the galactic center. We're moving at a brisk 510,000 miles per hour, but even at that speed, it takes us about 230 million years to complete one lap around the galaxy. Our path isn't a spiral heading inward. We are like a planet in a very, very distant orbit around a star. Our trajectory is stable for billions of years to come. We are not on a collision course. We will not be sucked in. Think of the galaxy not as a whirlpool, but as a majestic, slowly rotating carousel. We're one of the horses on the outer edge, and Sagittarius A is the central pillar. Our ride is smooth and steady. The gravitational pull of SGRA is crucial for holding the galaxy together on a large scale, but out here in our quiet suburban spiral arm, its direct pull is minuscule. The gravity of our stellar neighbors has a far greater effect on us. So while Sagittarius A* may be a monster, it is a distant one. It is the anchor of our galactic home, the silent ruler of a cosmic kingdom of which we are a very distant, very safe subject. We can study its weirdness and marvel at its power from a comfortable distance, secure in the knowledge that its chaotic life will not interfere with ours. The story of Sagittarius A is a testament to human curiosity, a journey from a mysterious hiss of static to a stunning photograph of a cosmic giant. What part of this story do you find the most mind-bending? Is it the star S2 moving at a fraction of the speed of light? The idea of an Earth-sized telescope? Or the fact that this spinning monster might be pointed right at us? Let us know in the comments below. And if you enjoy exploring the deepest mysteries of the cosmos, be sure to like this video and subscribe for more journeys into the unknown. From a hidden mystery to a revealed marvel, the journey to understand Sagittarius A is a perfect example of the scientific endeavor itself. For decades, it was a phantom, its existence inferred only by the ghostly dance of stars and a whisper of radio waves. It was a puzzle wrapped in layers of cosmic dust. But through decades of patient work, revolutionary technology, and the collaboration of thousands of minds across the globe, we have finally pulled back the veil. We now know that the heart of our galaxy holds a supermassive black hole of 4.3 million solar masses. We have seen its shadow, confirming a theory conceived a century ago. But this revelation isn't an end. It's a spectacular beginning. The image of Sagittarius A is not just a picture, it's a treasure trove of data that will keep physicists and astronomers busy for decades. Many mysteries remain. What is the true origin of supermassive black holes like ours? What causes its sudden, violent flares? What are those strange G objects that circle it? And what can its unique, possibly Earth-facing, orientation tell us about the fundamental physics of the universe? Future observations with an expanded Event Horizon telescope promise to answer some of these questions. They hope to create not just static images, but movies of the gas swirling into the event horizon, allowing us to see the maelstrom in motion. We are standing at the dawn of a new era of black hole astronomy, an era where we can directly observe and test the limits of physics in the universe's most extreme laboratories. The silent, invisible monster at the heart of our galaxy has finally shown its face. And it has proven to be a creature of immense complexity, a quiet giant with a chaotic soul, a testament to the fact that even in our own cosmic home, there are wonders and weirdness beyond our wildest imagination. The hunt for Sagittarius A* may be over, but the adventure of understanding it has just begun. The true scale of black holes will change how you see the universe. You're looking at a black hole. Well, you're looking at its shadow, cast against a brilliant backdrop of superheated plasma. You know it's big. You know it's powerful, an object so dense that not even light can escape its pull. You've heard the numbers, maybe thousands of times the mass of our sun. But let's be honest, the scale you're picturing in your head right now? It's not even close. The very words we use, big, massive, huge, they just don't work. They fail us. They become completely meaningless when you come face to face with the true nature of these cosmic monsters. We're not just talking about things that are large. We're talking about objects that force us to redefine the very concept of large. We're talking about gravitational wells so deep they literally shape entire galaxies. This is a journey to the edge of what's comprehensible, to a place where the sheer scale of things becomes so vast, so awe-inspiringly immense, it will fundamentally rewire how you see your place in the universe. So, forget what you think you know. The journey starts now. We'll start with what the universe calls small. Imagine a star, maybe 20 or 30 times more massive than our Sun, nearing the end of its life. For millions of years, it's been in a desperate, fiery war with its own gravity, fusing hydrogen to helium, helium to carbon, and so on. But it's a war it's doomed to lose. In its final moments, the core collapses. In less than a second, a mass greater than our Sun gets crushed down, and down, and down, beyond any limit we can imagine. It's a process so violent it tears a permanent hole in the fabric of space-time. What's left is a stellar mass black hole, the dead, silent heart of a once mighty star. It might have the mass of, say, 10 of our suns, but it's squeezed into a sphere of pure impossibility. If you could see its event horizon, the point of no return, it would only be about 60 kilometers across. You could drive that in under an hour. A black hole with the mass of several suns, crushed into a space smaller than most cities. Think about that for a second. The corpse of a star, taking up less space than your morning commute. But we're not staying small for long. Because on this trip, we're going where black holes don't just swallow stars. They eat entire solar systems for breakfast. The baseline: stellar death and cosmic seeds. To really get a feel for the scale we're about to encounter, we have to start from the ground up. The first rung on the ladder is the stellar mass black hole. They're the most common type in the universe, the seeds from which greater monsters grow. Our Sun is so big you could fit 1,000,000 Earths inside it. It makes up 99.8% of all the mass in our solar system. Now, imagine taking 3 of them, all that unimaginable mass, and crushing them. Not just compressing them, but forcing every single atom to break down. Protons, neutrons, electrons. All structure is just annihilated by gravity. The result is a singularity, a point of literally infinite density. Around this impossible point is the event horizon. It's not a surface you can touch. It's a boundary in space-time. Once you cross it, all possible paths lead to the center. The escape velocity, the speed you need to break free, is now faster than the speed of light. And since nothing can travel faster than light, nothing ever comes back. A black hole with 3 times the mass of our Sun would have an event horizon just 18 kilometers, or about 11 miles, in diameter. It's a jarring disconnect between mass and size. It has the gravitational pull of 3 suns, but a footprint smaller than a town. If you were to replace our Sun with a black hole of the exact same mass, something amazing would happen. Almost nothing. Earth and the other planets would just keep orbiting it. From our distance, the gravity would be identical. We'd freeze in eternal darkness, sure, but we wouldn't get sucked in. A black hole isn't a cosmic vacuum cleaner. Its real power is its density, not some magic long-range suction. You have to get dangerously close to be in real trouble. But when you do get close, the laws of physics start to twist in horrifying ways. As you approached the event horizon, the gravity pulling on your feet would be so much stronger than the pull on your head that you'd be stretched into a thin stream of atoms, a process astronomers poetically call spaghettification. Time itself would warp. To someone watching from far away, you'd seem to slow down, getting slower and slower as you neared the horizon, eventually looking frozen at the edge for eternity. But from your perspective, time would feel normal. You'd cross the horizon in a single moment, and in that instant, you might see the entire future of the universe flash before your eyes as you fall toward the singularity. These stellar mass black holes are everywhere. Our own Milky Way is thought to have at least 100 million of them, just silent wanderers in the dark. They are the ghosts of dead stars, the quiet aftermath of a supernova's violent scream. They're fascinating, they're terrifying, and on the scale of what's coming, they're basically nothing. They are just the opening act. The first jump: intermediate mass black holes, the missing link. For a long time, astronomy had a big puzzle. We could find the small black holes, the stellar mass ones, up to a few dozen times the mass of the Sun. And we could see the colossal ones, supermassive black holes with millions or billions of solar masses. But what about the ones in between? Where were the black holes with hundreds or thousands of solar masses? Where was the missing link? Finding them was like searching for a single grain of sand on a dark beach. A stellar mass black hole comes from one star. A supermassive one sits at the center of a galaxy, given away by the billions of stars orbiting it. But an intermediate mass black hole, or IMBH, doesn't have an obvious home. They're too big to form from a single star in today's universe, and too small to anchor a whole galaxy. For decades, they were just a theory. Scientists figured they could form in a couple of ways. Maybe in the chaotic hearts of dense star clusters, where stars are packed in like bees. A black hole forms, merges with another, then another, slowly snowballing its mass. Or maybe they were primordial seeds from the dawn of time, formed in the ultra-dense conditions of the early universe. But finding proof was tough. An isolated IMBH is almost perfectly invisible. So astronomers became detectives. They looked for the gravitational kick. A black hole would give a star that got too close, flinging it out of its home cluster at incredible speeds. They hunted for the X-ray flares that happen when one of these black holes tears a star apart. And slowly, the evidence started piling up. In 2019, gravitational wave observatories detected the merger of two black holes that created a new one with a mass of about 142 suns, the first definitive IMBH. Since then, more candidates have emerged. Evidence now points toward an IMBH of at least 200 solar masses in the Omega Centauri star cluster in our own Milky Way, and another with 100,000 solar masses in a dwarf galaxy. These discoveries are more than just filling a gap on a chart. They show us the pathway. They're the bridge between the death of a single star and the birth of a galactic monster. Let's try to picture one. A black hole of 10,000 solar masses. Its event horizon would be about 60,000 kilometers in diameter. That's about 5 times the diameter of the Earth. You could line up 5 Earths, side by side, and they would fit inside the shadow of this mid-sized black hole. But as mind-boggling as that is, we're about to leave the stellar realm and enter the galactic. The next jump in scale will make this 10,000 sun black hole seem tiny. The solar system breaker, Sagittarius A. For millennia, humans have looked up at that hazy, milky band of light in the night sky. We now know it's the disk of our home galaxy, a swirling city of over 200 billion stars. And for the last few decades, we've known something else. At the very heart of that city, 27,000 light years from us, there is a monster. Its name is Sagittarius A*, SGRA* for short. It's our galaxy's supermassive black hole. You can't see it directly. It's hidden by thick clouds of gas and dust. But we know it's there because we can see what it does to the stars around it. For years, astronomers have tracked stars at the galactic core, watching them whip around an invisible central point at unbelievable speeds. Imagine watching moths dance around an invisible flame. One star, S2, became the perfect test subject. It orbits this point once every 16 years, and at its closest approach, it accelerates to nearly 3% of the speed of light. That's over 8,000 kilometers per second. There's no star cluster, nothing, that could create that kind of gravity without collapsing into a single object. By using the orbits of these stars, astronomers calculated the mass of that object. The number they landed on is a staggering 3 million times the mass of our Sun. So how big is it? With a mass of 3 million suns. The event horizon of SGRA asterisk has a diameter of about 24 million kilometers. That number sounds big, but let's bring it home. Let's use our solar system as a ruler. Mercury, the closest planet to our Sun, has an orbit that's about 116 million kilometers wide. SGRA asterisk S event horizon, at 24 million kilometers across, would fit comfortably inside the orbit of Mercury. In fact, you could almost line up 5 of our galaxy's central black holes side by side inside the path Mercury takes around the Sun. This is where our frame of reference starts to break. The black hole at the center of our own galaxy, a beast of 3 million suns, is smaller than the orbit of our first planet. In 2022, the Event Horizon Telescope collaboration released the first ever image of SGRA. We didn't see the black hole itself, but its shadow, silhouetted against the glowing, swirling gas being heated to millions of degrees before its final plunge. And the size of that shadow, measured from 27,000 light-years away, perfectly matched the predictions for a black hole of that mass. The monster was real. For now, it's a relatively quiet monster, on a bit of a diet. But it's our anchor. It's the gravitational heart that our entire galaxy, including our Sun and every star you see at night, revolves around in a slow, 230 million year cosmic dance. The galactic anchor. M87. We've met a black hole that fits inside Mercury's orbit. It feels like we've hit a new peak of scale. But now, we have to reset our perspective completely. Sagittarius A asterisk, the heart of our galaxy, is about to look small. We're traveling 55 million light-years away to the Virgo galaxy cluster, to meet a true titan. The black hole at the center of galaxy Messier 87, or M87. M87 is a giant elliptical galaxy, far larger than our Milky Way. And its central black hole is in a totally different league. If SGRA is a lion, M87 is a leviathan. This is the black hole that became a global icon. In 2019, the Event Horizon Telescope collaboration released the very first direct image of a black hole's shadow, and M87 was their target. That glowing ring of fire around a perfect circle of darkness was humanity's first real look into the abyss. Why M87 and not our own black hole first? M87's black hole is over 1,000 times more massive, which makes its shadow appear larger in our sky, even though it's much farther away. When the team calculated its mass from that shadow, they arrived at a number that almost defies belief. 5 billion times the mass of our Sun. Let that sink in. 6.5 billion. We've just made a cataclysmic leap. So, what does that do to the scale? Let's go back to our solar system ruler. SGRA asterisk was 24 million kilometers across. M87's event horizon, with 5 billion solar masses, stretches 38 billion kilometers across. How big is that? Our entire solar system, out to Neptune's orbit, is about 9 billion kilometers across. The event horizon of M87 is over 4 times wider than our entire solar system. If you placed this black hole where our Sun is, its event horizon wouldn't just swallow Mercury, Venus, Earth, and Mars. It would swallow Jupiter, Saturn, Uranus, Neptune, and even the distant dwarf planet Pluto. Our entire planetary system would be gone in a cosmic gulp. Light, the fastest thing there is, would take over 35 hours to travel from one side of its event horizon to the other. This isn't just an object in a galaxy anymore. It's an object that defines its galaxy. Unlike the quiet SGRA asterisk, M87 is an active, ravenous engine. It furiously consumes gas and dust, and its powerful magnetic fields funnel some of that material into 2 colossal jets. These jets are blasted out from the black hole's poles at nearly the speed of light, extending for thousands of light years. We've seen them. It's a cosmic blowtorch powered by the monster at its core. We are now in the presence of an object so massive it makes our solar system look like a tiny speck. And yet, we're still climbing. We are about to meet a class of objects so vast that even the solar system swallowing M87 will feel like a stepping stone. The behemoths. The truly supermassive. We've broken the solar system scale. The mind is struggling for a new ruler. An object that can swallow Neptune's orbit feels like the limit. But the universe doesn't care about our imagination. Supermassive. Black holes start at 1 million solar masses, but the category has a very, very high ceiling. Let's push out to the Coma cluster, a dense swarm of over 1,000 galaxies. At the heart of one of its largest, NGC 4889, lurks a monster once thought to be a record holder. Its estimated mass is a mind-numbing 21 billion solar masses. 21 billion. That's more than 3 times the mass of M87. Its event horizon would be about 124 billion kilometers in diameter. Our solar system, at 9 billion kilometers across, is now a trivial measurement. You could line up almost 14 of our solar systems, end to end, across the shadow of this single black hole. Light itself would take nearly 2 full days to cross from one side of its event horizon to the other. These are ultramassive black holes, a special class for those over 10 billion solar masses. They are the kings of their domains, the gravitational anchors for entire clusters of galaxies. They didn't get this big by eating stars one by one. They grew by cannibalism, galaxy swallowing galaxy, with their central black holes spiraling together in a deadly dance for millions of years, until they merge in a cataclysm that sends gravitational waves shuddering through space-time. We've seen a cosmic hierarchy in action. Stellar black holes are the seeds. Supermassive ones like SGRA* are the hearts of galaxies. And ultramassive ones like M87 and NGC 4889 rule galactic empires. Each step has forced us to abandon our yardsticks. We went from cities, to planets, to solar systems. Now, even our solar system is too small to be a useful measure. The scale has become architectural. These aren't just things, they're places. Vast, dark places from which there is no escape. And we still haven't reached the top. There is one final peak to climb. The climax. The universe breaker, ton 618. Prepare yourself. Every comparison we've made is about to fall apart. We're now traveling 8 billion light years away, looking back in time to when the universe was young. We're looking at an object that defies explanation. Its name is ton 618. When it was first catalogued in 1957, it just looked like a faint blue star. But in 1970, radio emissions were detected, and astronomers realized they were looking at a quasar, the most energetic and luminous phenomenon in the known universe. A quasar is what you get when an ultramassive black hole is in the middle of a feeding frenzy. The material spiraling into it forms a massive accretion disk, which heats up and shines with an intensity that can outshine its entire galaxy 1,000 times over. The light from ton 618 is estimated to be 140 trillion times brighter than our Sun, making it one of the most brilliant objects in the cosmos. That incredible brightness allows us to measure the speed of the gas clouds swirling around the central engine. And from those speeds, astronomers calculated the mass of the black hole powering it all. The number they landed on is 66 billion solar masses. 6 billion. Let's just pause there. Our home black hole, SGRA*, is 3 million. M87, the solar system swallower, is 5 billion. Ton 618 is 10 times more massive than M87. It's more than 15,000 times more massive than our own galaxy's central black hole. So, what is its size? The event horizon of Ton 618 has a diameter of roughly 390 billion kilometers. Our entire solar system, out to Neptune, is 9 billion kilometers across. You could fit our whole solar system inside Ton 618's event horizon, then do it again and again. You could fit our solar system inside its shadow more than 40 times over. Light would take nearly 2 weeks to cross the diameter of this single object. We're no longer talking light hours or light days. Its point of no return is measured in light weeks. TON 618 is so extreme, it challenges our models of how galaxies even form. How could a black hole get this big, this fast, in the early universe? It suggests that maybe, in the primordial cosmos, some black holes were born from the direct collapse of unimaginably vast clouds of gas, skipping all the intermediate steps. While there are candidates for even more massive black holes out there, like Phoenix A, their mass is estimated indirectly. As of today, Ton 618 holds the record as the most massive black hole ever directly measured. It is the undisputed king. We've reached the top of the ladder. We've gone from a black hole the size of a city to one that could swallow dozens of solar systems. We have nowhere left to go up. There is only the long look back down. The brain rewiring. So, where does that leave us? We started this journey trying to understand the true scale of black holes. We began with a dead star crushed into the size of a city. We climbed a ladder of mass, meeting our galaxy's heart, SGRA*, and were shocked to find it smaller than Mercury's orbit. We journeyed to M87 and found something that could swallow our entire solar system whole. And we ended at Ton 618, a monster so colossal our solar system is just a speck in its shadow, a beast whose very existence pushes our understanding of the cosmos to its limit. The words, big, and massive, have been stretched until they snapped. You now carry a new mental yardstick, one calibrated against the terrifying and majestic reality of these objects. The black holes we've seen aren't just things in the universe. They are the forces that shape it. They are cosmic architects, the anchors for galaxies, the engines of creation and destruction. They are the points where our laws of physics crumble and where space and time itself begin to warp. Now, when you look up at the night sky, at that faint river of the Milky Way, you know what's waiting at its heart. You know it's just one of many, a relatively small player in a cosmic game of titans. And that new perspective, that sense of profound, almost dizzying awe, isn't something to fear. It's something to embrace. It's the feeling of seeing the universe, for just a moment, as it truly is. Vast, strange, and more magnificent than we ever could have imagined. If this video rewired your perspective on the universe, subscribe for more journeys into the cosmos. The universe is full of wonders just waiting to be understood. Thanks for joining us on this exploration of scale. Keep looking up. What happens when you turn the sun into a black hole? What would happen if, in a blink, our sun was crushed down into a black hole? Your first thought, that deep, primal fear, is that Earth would be instantly and violently sucked into a cosmic abyss. It's the stuff of nightmares. An unstoppable, gravitational monster suddenly appearing in the heart of our solar system. But the truth is far stranger, and way more interesting. For the first 8 minutes and 20 seconds after the sun becomes a black hole, absolutely nothing would change. We'd keep orbiting an empty spot in space, basking in the light of a star that was already gone. We'd be completely, blissfully unaware of the catastrophe. And then, sudden, absolute darkness. The sky would snap to black. That familiar, life-giving warmth would vanish, replaced by the chilling silence of interstellar space. And yet, we still wouldn't get sucked in. Our planet would just keep going on its path, loyally orbiting a ghost. Understanding why this happens, why our intuition is so wrong, isn't just about solving a weird hypothetical. It's about unlocking a fundamental secret of the universe. It's a simple rule that governs the life and death of stars and the shape of galaxies, and it lets us finally, truly wrap our heads around the most powerful objects in existence. The last light. For us on Earth, the moment our sun collapses is a total non-event. Life goes on as normal. People go about their day, traffic is flowing, birds are singing. But 150 million kilometers away, a drama of unimaginable violence has just unfolded. The star that anchored our solar system for 4.5 billion years, a colossal sphere of plasma over 1 million kilometers wide, has been squeezed past its breaking point. In this scenario, the sun has been compressed into an object with a radius of just 3 kilometers. A star has been replaced by something the size of a small city. As this happens, the very last photons of light from our sun begin their final journey. They stream away from where the star's surface used to be, a wave of light expanding outwards at nearly 300,000 kilometers per second. This isn't a flicker or a dimming. It's an abrupt, instantaneous stop. One moment, the sun is a roaring nuclear furnace. The next, there is only a tiny, silent point of infinite density. For 8 minutes and 20 seconds, that final wave of sunlight travels across the void. It races past Mercury, then Venus. Here on Earth, we see the sun exactly as it was 8 minutes ago. A perfect, glowing orb in the sky. We feel its warmth. Solar panels keep generating electricity, and plants continue their silent, vital work of photosynthesis, with no idea that their power source has already been extinguished. And it's not just light. The sun constantly throws a stream of charged particles at us, called the solar wind. This wind travels much slower than light, so we'd still feel its effects for a day or two. But the sun also makes a torrent of ghostly particles called neutrinos. They're so ethereal they pass through almost all matter as if it wasn't even there. Trillions are passing through you, through the entire planet, every single second. Their trip from the sun's core to Earth also takes about 8 minutes. So as we stand here, under the light of a dead star, the last neutrinos from its defunct core are already washing over us. Then, the moment arrives. 8 minutes and 20 seconds after the sun's collapse, the wavefront of darkness hits our planet. It's not a sunset. It's not an eclipse. It is the sudden, jarring removal of our main source of light. The sky turns from brilliant blue to pitch black in an instant. The moon, which only shines by reflecting sunlight, vanishes. The only things left are the cold, distant points of the stars, and the faint glow of other planets which will themselves wink out one by one as their own time delay catches up. From Jupiter, it would take over 40 minutes for the sun to disappear. From Neptune, over 4 hours. An observer on the Voyager 1 probe, deep in interstellar space, wouldn't see the sun die for nearly a full day. On Earth, the psychological shock would be immediate and profound. Imagine every light in the world going out at once, but on a planetary scale. The anchor of our reality, the sun in the sky, is just gone. We're plunged into a night deeper than any human has ever known. And in that terrifying, silent darkness, we'd all be asking the same question. When do we fall in? The unchanged orbit and the nature of gravity. This is the great misconception, the plot hole in 1,000 disaster movies. The idea that a black hole is a cosmic vacuum cleaner is deeply ingrained in our minds, but it's fundamentally wrong. Out here, at a safe distance of 150 million kilometers, Earth's orbit would remain almost completely unchanged. The planets would continue their celestial dance around a point of darkness where the sun used to be. To understand why, we need to know what gravity actually is. For centuries, our best explanation came from Isaac Newton. He saw gravity as a force, an invisible rope tying objects to one another. The strength of that rope, he figured, depends on two things: how massive the objects are and how far apart they are. In our scenario, the sun has been crushed into a tiny volume, but its mass, the total amount of stuff it's made of, hasn't changed. It's still one solar mass. And the distance between Earth and the center of that mass hasn't changed either. So, according to Newton, the gravitational force is exactly the same. The invisible rope pulling on Earth has the same strength it always did. As far as our planet is concerned, it can't tell the difference. It feels the same tug, so it stays in the same orbit. But Newton's picture, while incredibly useful, isn't the whole story. In the early 20th century, a young patent clerk named Albert Einstein gave us a revolutionary new way to see gravity. He realized gravity isn't a force at all. It's a consequence of mass and energy warping the very fabric of the universe, a four-dimensional fabric he called space-time. Imagine space-time as a stretched rubber sheet. A massive object like the sun creates a deep dent in this sheet, like a heavy bowling ball. Planets like Earth aren't being pulled by a rope. They're simply following the straightest possible path through this curved space-time, like a marble rolling around the edge of the dent. That's what an orbit is. When our sun collapses into a black hole, it's like swapping the bowling ball with another one of the asterisk exact same weight, but one that's much, much smaller. Out here, far away from the center, the curve in the rubber sheet is identical. The slope our Earth is rolling on hasn't changed. So, our orbit stays stable. The only thing that changes is the shape of space-time very close to the center. Where the sun's surface used to be, the curve was relatively gentle. Now, with all that mass packed into a single point, the dent in the rubber sheet becomes almost infinitely steep right at the center. It's no longer a gentle dimple. It's a bottomless well. This is the essence of a black hole. A region of space-time so severely warped that, once you're in, all paths lead down. But you have to get very, very close to fall into that well. For a black hole with the mass of our sun, that point of no return is just 3 kilometers from the center. Outside that tiny sphere, gravity behaves exactly as it always did. Mercury, Venus, Earth, and Mars would all just keep orbiting, oblivious to the fact they're now circling a singularity instead of a star. We wouldn't get sucked in. We'd just be left to freeze in the dark. The breaking point. The Schwarzschild radius. Every single object in the universe, from an atom to a speck of dust, to you, to the Earth, to the sun itself, has a breaking point. A point of no return. It's a specific size, a critical radius, that it would need to be crushed into for its own gravity to become so strong that it collapses on itself and forms a black hole. This critical size is called the Schwarzschild radius. The idea came from a German astronomer named Karl Schwarzschild, in the most unlikely of places. In 1915, while serving on the Russian front during World War I, Schwarzschild got his hands on Einstein's brand new theory of general relativity. In between calculating artillery trajectories, he started playing with the equations. Within months, he had found the first exact solution to Einstein's field equations, describing space-time around a single point of mass. Tragically, Schwarzschild wouldn't live to see what his discovery meant. He died in 1916 from a disease he contracted at the front. But his calculations laid the mathematical foundation for black holes. What Schwarzschild found is a direct link between an object's mass and the size of its event horizon, the boundary from which not even light can escape. The formula is beautifully simple. The Schwarzschild radius is just a couple of universal constants multiplied by the mass of the object. What this really means is that the Schwarzschild radius is directly proportional to the mass. The more massive something is, the bigger its Schwarzschild radius. This isn't just an abstract equation. It gives us a real, physical size for any amount of mass. It tells us exactly how small you'd need to crush something to turn it into a black hole. And the sizes are shocking. Let's start with our Sun. It has a mass of about 2 nonillion kilograms. If you plug that into Schwarzschild's equation, you get a radius of about 3 kilometers. Think about that. Our Sun, a star so vast you could fit over 1 million Earths inside it, would need to be compressed into a sphere with a diameter of just 6 kilometers, the size of a small town, to become a black hole. All of that unimaginable mass, inside a space you could drive across in minutes. Now what about Earth? Our planet has a mass of about 6 septillion kilograms. What's its breaking point? If you crushed the entire Earth, mountains, oceans, molten core and all down to its Schwarzschild radius, it would be a sphere just 9 millimeters in radius. Smaller than a marble. The mass of a planet, compressed into something you could hold in your hand. We can even do this for a person. A 70-kilogram human also has a Schwarzschild radius. To become a black hole, you'd need to be compressed into a space with a radius of about 10 to the negative minus 25 meters. That number is so small it's basically meaningless. It's trillions of times smaller than a single proton. The universe just doesn't have a way to do that. So this is the simple, universal rule. A black hole isn't defined by what it is, but by how much mass is packed into how little space. The Sun isn't massive enough to collapse into a black hole on its own. It would need to be about 20 times heavier for that to happen naturally. But if you could somehow compress it, its breaking point is a sphere just 6 kilometers across. This tiny, almost laughably small size for something as massive as our Sun is the key. It's the unit of measurement we can now use to understand the true titans of the cosmos. By knowing just how small a solar mass black hole is, we can finally begin to appreciate the scale of the universe's real monsters. The supermassive black holes. The true scale of black holes. Okay, so we have our baseline. A black hole with the Sun's mass is a tiny, invisible object just 6 kilometers across. It's incredibly dense, but on a cosmic scale, it's a pinprick. Most stellar mass black holes, the kind made from collapsing giant stars, are in this range, maybe 5 to 20 times the Sun's mass, with event horizons a few dozen to a couple hundred kilometers across. They're powerful, but they're small. These, however, are not the black holes that run the universe. At the heart of nearly every big galaxy, including our own Milky Way, there lurks a completely different beast. A supermassive black hole. Let's start at home. At the center of the Milky Way, about 26,000 light-years away, sits Sagittarius A. That's Sagittarius A star. For decades, astronomers watched stars at the galactic center whipping around an unseen point at insane speeds. One star, S2, was seen moving at up to 2.5% the speed of light as it orbited this mystery object. By using the same laws of orbital mechanics that govern our planets, they could calculate the mass of the thing it was orbiting. The number was staggering. Sagittarius A* has a mass of about 3 million times our Sun. 3 million suns, all in a single point. And because more mass means a bigger Schwarzschild radius, just how big is it? The diameter of Sagittarius A*'s event horizon is about 23.5 million kilometers. That number is so big it feels fake, so let's put it in perspective. The distance from our Sun to its innermost planet, Mercury, is about 46 million kilometers. This means the entire event horizon of our galaxy's supermassive black hole could comfortably fit inside the orbit of Mercury. On May 12, 2022, the Event Horizon Telescope team released the very first image of Sagittarius A. After years of work, combining data from radio telescopes across the globe, they gave us a picture of the glowing gas swirling around the black hole's shadow. For the first time, we saw the monster in our own backyard. But Sag-A is, by cosmic standards, pretty modest. Let's scale up. Take the galaxy Messier 87, whose black hole was the first one ever imaged. This behemoth weighs in at about 6.5 billion solar masses. Our tiny 6-kilometer sun-sized black hole is a grain of sand next to this thing. The event horizon of M87's black hole is so big that a beam of light, the fastest thing there is, would take 2.5 days just to cross its shadow. And even M87 isn't the king. For that, we have to look across the universe to a distant object called TUN 618. When it was first spotted in 1957, astronomers thought it was just a faint blue star. Only later did they realize they were seeing the hyperluminous glare of a quasar, an intensely bright beacon powered by a black hole furiously eating gas and dust. And the black hole at its heart is one of the most massive ever found. Current estimates put the mass of TUN 618 at a mind-boggling 40 to 66 billion times the mass of our Sun. Astronomers had to invent a new term for it: an ultramassive black hole. To put that into perspective, if you took every single one of the hundreds of billions of stars in our entire Milky Way galaxy and crushed them into a single point, you would still be short of the mass of TUN 618. Its Schwarzschild radius is enormous. Its diameter stretches for billions of kilometers. A beam of light wouldn't take days to cross its shadow, but weeks. If you placed TUN 618 at the center of our solar system, its event horizon would swallow every planet, reaching far beyond the orbit of Neptune. That is a scale that's almost too big to think about. These objects make us question how black holes can even get this big. They're probably the result of eons of galactic mergers, with smaller black holes combining over and over. And sometimes, that process gets stuck in a spectacular way. In a galaxy called B20402+379, astronomers found what looks like the most massive pair of black holes ever seen. It's two supermassive black holes, with a combined mass of 28 billion suns, orbiting each other just 24 light-years apart. They are locked in a cosmic dance that seems to have been going on for over 3 billion years without them merging, a perpetual, titanic waltz. From the 6-kilometer pinprick of our sun-turned black hole, to the city-sized stellar ones, to the one that fits inside Mercury's orbit, all the way to the solar system swallowing Titan TUN 618. The simple rule of the Schwarzschild radius is the thread connecting them all. It gives us a ladder of scale that lets our minds climb from the things we can understand to the things that are truly incomprehensible. The long, cold night. So let's go back to our lonely planet, Earth, faithfully orbiting that tiny, dark point where our sun used to be. The initial shock of darkness gives way to a new, and much deadlier reality: the cold. Without the sun's constant energy, Earth's temperature would start to plummet. The planet would just radiate its heat away into the freezing void of space. Within a week, the average global surface temperature would drop below freezing. After a year, it would be a devastating -73 degrees Celsius, or -100 Fahrenheit. Eventually, the planet would settle around -240 degrees Celsius, -400 degrees Fahrenheit, a point where the faint heat coming from Earth's core finally balances out the heat it loses to space. For life, the consequences would be swift and brutal. The first to go would be photosynthesis. Without sunlight, most plants on the surface would die within weeks. This would trigger a catastrophic collapse of the food chain. Herbivores would starve, followed quickly by carnivores. The oceans would put up a slightly longer fight. The surface would freeze over pretty fast, but that layer of ice would act as an insulator, protecting the deep ocean from the killing cold above. The oceans might not freeze solid for hundreds of thousands of years. Could anything survive? Maybe. Deep in the oceans, near hydrothermal vents, entire ecosystems exist that don't need sunlight. They get their energy from the heat and chemicals spewing from the Earth's crust. These communities of extremophiles, bacteria, tubeworms, and other strange creatures might just keep on thriving in the dark, with no idea that the world above them has died. And what about us? Survival on the surface would be impossible. The cold and darkness would be absolute. Our only hope would be to go deep underground. We'd have to build self-sustaining bunkers, powered by the Earth's own geothermal heat. Nuclear power could also work, for as long as we had fuel. Life would become a cramped, difficult existence in artificially lit caverns. We'd become a species of deep Earth dwellers, telling stories about a mythical time when the sky was blue and a great golden orb warmed the world. Above, the surface of the Earth would be a frozen, silent museum, a tombstone planet coasting through the eternal night, forever tethered by gravity to the ghost of its dead star. This whole journey, from our sun to a 6-kilometer black hole, and from there to the solar system-sized titans in distant galaxies, shows us something profound about the universe. The laws of physics are the same everywhere. The same rule, the Schwarzschild radius that tells us our sun's breaking point, also lets us measure and understand the most extreme objects we've ever found. It turns black holes from mythical monsters into predictable, physical objects. They aren't cosmic vacuum cleaners. They're just the ultimate expression of mass-bending spacetime. By imagining the impossible, turning our sun into a black hole, we've found the tools to grasp what's really possible out there. We can now look at an image of Sagittarius A*, or read about the insane mass of Ton 618 and have a real sense of scale. The universe isn't just strange, it's also elegant and consistent. So the next time you look up at the sun, remember its hidden nature. Remember its breaking point, the size of a city. And remember that this simple fact is your key to understanding the mind-bending scale of everything else. If you've ever wondered what would happen if you actually fell into a black hole, check out our next video on that very topic right here. And for more explorations into the biggest questions in the cosmos, make sure you subscribe. The black hole that could swallow 40 billion suns. Imagine an object so massive it could swallow our sun. Now imagine it swallowing 1,000 suns. 1,000,000. 1,000,000,000. Keep going. Imagine an object so profoundly dense, so gravitationally dominant, that it could swallow our sun 40 billion times over. And not even leave a trace. This isn't science fiction. These objects are real. They're the universe's ultimate monsters, lurking in the dark, silent voids between galaxies, and at the very heart of galaxies themselves. They are the upper limit of cosmic horror, objects that defy our sense of scale and stretch the laws of physics to their breaking point. Today, we are not just talking about black holes. We're going on a hunt for the most extreme, the most massive, the most terrifying black holes that exist. We will journey from the familiar scale of our own solar system to the unfathomable edges of cosmic possibility. We'll explore the mind-bending science that allows these beasts to grow to such terrifying sizes, and we'll confront what their existence tells us about the past, present, and ultimate fate of our universe. This is a search for the black hole that could swallow 40 billion suns. Let's try a little thought experiment. Picture our sun, a star so vast that over 1,000,000 Earths could fit inside it. Now, watch as it's pulled, stretched, and devoured by a point of absolute darkness. One sun, gone. Now, picture 2, 10, 100, 1,000. Watch as a torrent of stars, a river of 1,000,000,000 suns, is funneled into that same, insatiable point. Now, 40 billion. A number so large it's just a sound without real meaning. 40 billion suns, erased from existence. These cosmic monsters are real. And we're going on a hunt to find them, to understand their terrifying size, and to uncover what they tell us about the very limits of our universe. The anatomy of a monster. Before we can hunt the titans, we have to understand the nature of the beast. What is a black hole? Put simply, it's a place where gravity has become so overwhelmingly strong that nothing, not even light, can escape. But that simple answer hides a universe of complexity. The story of a black hole begins with the death of a truly massive star. Not a star like our Sun, which will one day swell into a red giant and then peacefully fade into a white dwarf. No, we're talking about stars many times more massive. When these stellar giants run out of nuclear fuel, the outward pressure from their fusion furnace suddenly stops. With nothing to hold it up, the star's immense gravity takes over, and it collapses in on itself in a catastrophic implosion. This collapse triggers a supernova, one of the most violent events in the universe, blasting the star's outer layers into space. What's left behind is the crushed, hyper-dense core. If this core is massive enough, its gravity is so intense that it just keeps collapsing, squeezing an immense amount of matter into an infinitely small point. This is the singularity. Surrounding this singularity is the feature that gives a black hole its name: the event horizon. The event horizon isn't a physical surface you could touch. It's a boundary in space-time, a point of no return. Anything that crosses this boundary, a planet, a star, a particle of light, is irrevocably captured by the black hole's gravity and will inevitably fall toward the singularity. From our perspective, it's the edge of the observable universe. Information can't get out. Now, you might think black holes are cosmic vacuum cleaners, actively sucking in everything around them. They're not. If you were to replace our Sun with a black hole of the exact same mass, Earth and the other planets would continue to orbit it just as they do now, though it would get very, very cold. A black hole's gravitational pull is only inescapable once you get dangerously close, once you cross that fateful line of the event horizon. The physics here is governed by Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of spacetime. Imagine a flat, stretched-out rubber sheet. A small marble, the Earth, creates a small dimple. A bowling ball, the Sun, creates a deeper one. Now, imagine an object so heavy it punches a hole straight through the sheet, creating a well with no bottom. That's a black hole. It's a place where space-time has been warped to such an extreme that all paths lead inward. This warping of space-time isn't just a theoretical concept, we can actually see it. We can see the light from distant stars being bent and distorted as it passes near a massive object, an effect called gravitational lensing. It's one of the key ways astronomers can find and even weigh these otherwise invisible monsters. Another spectacular and terrifying consequence of this extreme gravity is a process known by the wonderfully descriptive name, spaghettification. As an object, say a hypothetical astronaut, gets too close to a black hole, the gravitational pull on their feet would be so much stronger than the pull on their head that they would be stretched vertically and squeezed horizontally, like a noodle of pasta, before being torn apart atom by atom. So, we have the basic ingredients. A singularity of infinite density, an event horizon marking the point of no return, and a gravitational field so powerful it warps the very fabric of reality. These are the fundamental properties of all black holes. But as we're about to see, they come in a truly staggering range of sizes. The journey of scale begins. Our hunt for the 40 billion solar mass monster has to start with a sense of scale. And to build that scale, we begin with the small ones, stellar mass black holes. These are the direct remnants of massive, collapsed stars, the kind we just discussed. The first object widely accepted to be a black hole was Cygnus X1, confirmed in the early 1970s. It clocks in at around 21 times the mass of our Sun. In the grand scheme of things, this is a baby. The lightest known black hole is only about 3.8 times the Sun's mass. There are likely hundreds of millions of these stellar mass black holes quietly drifting through our own Milky Way galaxy, the silent ghosts of stars long dead. But these are just the first step on the ladder. For decades, astronomers were faced with a puzzle. They saw the small stellar mass black holes, and they saw the giants at the centers of galaxies, but there seemed to be a gap in between. This led to the search for intermediate mass black holes, or IMBHs. These would be the missing link, with masses from a few hundred to a few 100,000 times that of our Sun. Finding them has been incredibly difficult. The current theory is that they might form in the dense hearts of ancient star collections called globular clusters, through a series of runaway stellar mergers. Or perhaps they're the seeds from which their larger cousins grow. While evidence is mounting, they remain one of the most elusive targets in astrophysics. But it's the next step up the scale where things get truly mind-boggling. We now enter the realm of the supermassive black holes, or SMBHs. As their name implies, we're talking millions, or even billions, of solar masses. And the evidence is now overwhelming. Almost every large galaxy, including our own Milky Way, has one of these behemoths lurking at its center. Our galaxy's monster is named Sagittarius A*, pronounced a star. It lies about 26,000 light-years from Earth, hidden from our direct view by thick clouds of gas and dust. But we know it's there. For years, astronomers tracked the frantic orbits of stars near the galactic center. One star, S2, was seen whipping around an unseen point in an orbit that takes just over 15 years. By precisely measuring the orbits of these stars, astronomers could calculate the mass of the object they were all circling. The result was undeniable. There had to be an object with about 4 million times the mass of our Sun packed into a space smaller than Mercury's orbit. The only thing that fits that description is a supermassive black hole. This discovery was so profound it was awarded the Nobel Prize in Physics in 2020. 4 million suns. Let that sink in. The event horizon of Sagittarius A* would stretch about 12 million kilometers across. That's vast, but in cosmic terms, it's still relatively small. So, our own galaxy's central black hole is a certified monster. 4 million suns, crushed into a singularity. It's the gravitational anchor that helps hold our entire galaxy together. And yet, on the cosmic scale we're exploring today, Sagittarius A is barely a blip. It's a foothill at the base of a colossal mountain range. The true giants make it look like a grain of sand. The first giants. Entering the ultramassive realm. Our journey has taken us from stellar mass black holes to the impressive 4 million solar mass heart of our galaxy. But now, we leave the familiar behind. We're about to enter a new classification, the ultramassive black hole. This is a term for black holes that exceed 10 billion solar masses. And our first stop is one of the most famous black holes in history. Travel 55 million light-years away to the Virgo galaxy cluster, and you'll find Messier 87, or M87, a colossal elliptical galaxy far larger than our Milky Way. At its heart lies a beast. This is the black hole that became a global icon in 2019 when the Event Horizon Telescope released the first ever direct image of a black hole's shadow. That stunning, fiery orange ring of superheated plasma circling a void of pure blackness was the shadow of the M87 black hole. And it is immense. Analysis of that image and the motion of gas around it puts its mass at about 4 billion times the mass of our Sun. That's over 1,000 times more massive than Sagittarius A. But that's still just the warm-up. Let's journey much farther, about 700 million light-years away, to a galaxy cluster named Abell 85. At its center is a supergiant elliptical galaxy called Holmberg 15A. For a long time, astronomers noticed its core was unusually faint, as if something had scoured the stars from its center. That something is a titan. Using the Very Large Telescope, astronomers traced the motion of stars deep within Holmberg 15A's core. The stars were moving at incredible speeds, orbiting a central mass of staggering proportions. The result of their direct measurement was a black hole with an estimated mass of 40 billion suns. Let that number sink in. 40 billion. This single object is one of the most massive black holes ever found, with a direct measurement, and weighs as much as 2/3 of all the stars in our Milky Way galaxy combined. It is 10,000 times more massive than Sagittarius A. What's more, this monster is what astronomers call a fossil. It's likely the result of dozens of galactic mergers over cosmic history. As the Abel 85 cluster formed, galaxies would have collided, their central black holes spiraling inward until they too combined. Holmberg 15A is the quiet end product of that violent past. It's also an outlier. It's 4 to 9 times larger than models predict for a galaxy of its type, challenging our understanding of how galaxies and their black holes co-evolve. But even this 40 billion solar mass titan has competitors for the throne. Our hunt must now take us to the very edge of the observable universe, to a time when the cosmos was much younger and more violent. We're going to meet the quasars, the reigning monarchs of mass. We've met Holmberg 15A, a 40 billion solar mass quiet giant. Now, our journey takes a dramatic turn. We are heading into the deep past, looking so far out that the light from our next target has been traveling for around 10.8 billion years to reach us. We are seeing an object named TUN 618 as it was when the universe was still in its youth. Today, we know TUN 618 is a hyperluminous quasar, essentially a supermassive black hole in the middle of a colossal feeding frenzy. As vast clouds of gas fall towards it, they form an incandescent vortex of matter called an accretion disk, heated to millions of degrees and releasing an unbelievable amount of energy. This makes the quasar shine with a luminosity 140 trillion times brighter than our Sun, making it one of the brightest objects in the entire universe. By analyzing the light from this accretion disk, astronomers can measure how fast the gas is moving. The gas around TUN 618 is screaming inwards at up to 7,000 kilometers per second, a testament to the unbelievable gravity at play. From these measurements, astronomers have calculated its mass. The most widely cited figure places TUN 618 at a staggering 66 billion times the mass of the Sun. Some estimates are a bit lower, but even the conservative end puts it in the highest echelon of cosmic monsters. The scale is almost impossible to comprehend. This single black hole is over 15,000 times more massive than Sagittarius A. Its event horizon is estimated to have a diameter so large you could fit our entire solar system out to the orbit of Neptune inside it. 11 times over. And TUN 618 is not alone. In a galaxy cluster 5.7 billion light-years away sits Phoenix A. Now, to be clear, its mass hasn't been measured directly. But based on models of its galaxy's properties, its central black hole could be gargantuan, with some estimates pushing as high as 100 billion solar masses. If those estimates hold, its event horizon would be vast enough to engulf the orbit of Pluto 100 times over. More recently, a new contender has emerged, found using a clever combination of techniques. Known as the cosmic horseshoe, it's a massive galaxy that acts as a powerful gravitational lens, bending the light of an even more distant galaxy into a near-perfect ring. By combining the lens model with observations of the stars in the foreground galaxy, astronomers made a stunning discovery. At the center of the lensing galaxy lies a dormant black hole with a precisely measured mass of 36 billion solar masses. This is remarkable because the black hole is not actively feeding. Its presence was betrayed purely by its immense gravity, proving that these monsters can be found even when they are silent and placing it firmly among the largest black holes ever reliably measured. The cosmic growth spurt and the ultimate limit. We've met the monsters. Now we have to ask, how did they get so big? A single star collapsing can't create a billion solar mass black hole. The growth of these ultramassive objects is a story of epic violence and relentless consumption. There are two primary pathways: feasting and fighting. The fighting path is through mergers. The universe is a dynamic place, and galaxies constantly collide. Our own Milky Way is on a collision course with Andromeda, set to merge in about 4-5 billion years. When two galaxies merge, their central supermassive black holes begin a long, gravitational dance, eventually coalescing into a single, more massive black hole. Holmberg 15A, at 40 billion solar masses, is believed to be the product of this exact process. The second growth method is feasting. The direct accretion of gas. This is what powers quasars like Ton 618. In the early, dense universe, vast filaments of cold gas flowed directly into the centers of young galaxies, providing an enormous food supply for their central black holes. But this feeding frenzy can't last forever. This leads us to the question of an upper limit. Can a black hole grow indefinitely? The answer appears to be no. There seems to be a theoretical maximum mass for an actively feeding black hole, a cap estimated to be around 50 billion solar masses. This limit isn't imposed by some new, exotic physics, but by the black hole's own destructive eating habits. As a black hole eats, the intense radiation from its ultra-hot accretion disk acts like a powerful wind, blasting away its own food supply. The more it eats, the more energy it radiates, and the harder it becomes to pull in more gas. This is what makes an object like Ton 618, with its estimated 66 billion solar masses, so fascinating. It appears to be above this theoretical limit. This could mean the limit is higher for spinning black holes, or that our understanding of accretion at these extremes is incomplete. Discoveries of dormant giants like the cosmic horseshoe's black hole, which sits right near this limit, help scientists test these models. The hunt for even bigger black holes is a hunt to see if this theoretical limit holds, or if the universe has found a way to break its own rules. The purpose of a monster. What do they tell us? We've journeyed across the cosmos and seen black holes with the mass of 4 million, 5 billion, and even 40 billion suns. It's easy to see them as cosmic oddities, but the truth is they're fundamental architects of the universe. For decades, astronomers have observed a tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, a relationship known as the M-sigma relation. This implies a deep, co-evolutionary link. A galaxy and its black hole grow together, influencing one another. When a supermassive black hole is in its active, quasar phase, the immense energy blasting out from its accretion disk can heat up and expel gas from the entire galaxy, temporarily shutting down star formation. This process, known as AGN feedback, is a critical component in modern models of galaxy evolution. It explains why the most massive galaxies often stop forming new stars. But the ultramassive black holes are pushing these theories to their limits. Objects like Holmberg 15A and the black hole in the cosmic horseshoe are found to be significantly more massive than the M-sigma relation predicts for their host galaxies. This suggests that at the highest mass scales, the rules might change, perhaps dominated by violent mergers rather than steady gas accretion. These giants also serve as unparalleled laboratories for testing the laws of physics. Measuring a 36 billion solar mass black hole through gravitational lensing is a powerful confirmation of Einstein's general relativity. Studying the light from quasars like Ton 618 allows us to probe the conditions of the early universe. And testing the 50 billion solar mass limit tells us about the intricate physics of accretion. The hunt is far from over. The James Webb Space Telescope is already finding surprisingly massive black holes growing at an accelerated pace in the early universe. New observatories, like the Vera C. Rubin Observatory, are poised to scan the sky with unprecedented speed. Once fully operational, it's expected to produce millions of alerts every single night, flagging everything from new asteroids to glowing supermassive black holes. These surveys will undoubtedly uncover more of the universe's most massive objects. This journey into the realm of cosmic monsters reveals a universe that is more extreme, more violent, and more magnificent than we often imagine. Each discovery pushes the boundaries of our knowledge and forces us to ask deeper questions. If a 40 billion solar mass black hole exists, what about a 70 billion? Or 100 billion? Exploring these questions is what drives science forward. If you find this journey into the cosmic unknown as fascinating as we do, consider subscribing and joining our community of explorers. There are countless mysteries left to uncover, and we plan to investigate them all. Let us know in the comments which cosmic mystery you'd like us to tackle next. We began with a simple, terrifying image. A black hole that could swallow 40 billion suns. We've journeyed through space and time and found that this is not a hypothetical concept. It is a reality. In the heart of the galaxy Holmberg 15A, such a monster sits in silent testament to a violent past. In the distant quasar Ton 618, an even larger beast may be shining with the light of its gargantuan meal. These objects are more than just cosmic record holders. They are the endpoints of galaxy formation, the physical manifestation of gravity taken to its ultimate extreme. They challenge our theories, anchor the galaxies we call home, and remind us of the sheer scale and power of the cosmos. So, the next time you look up at the night sky, at the countless points of light scattered across the darkness, remember the voids in between. Remember that out there, in the silent, immense dark, there are objects that hold more mass than all the stars in our galaxy. They are the black holes that could swallow 40 billion suns, the true monsters of the deep. And the hunt to understand them has only just begun. Finding the true monster of the universe. Our universe is a place of breathtaking beauty and, as we're about to find out, unimaginable scale. From our little home on Earth, we look out at the cosmos and see a familiar dance of planets, stars, and galaxies. We've measured their distances, we've weighed their masses, and we've learned their secrets. We've charted the arms of our own Milky Way, this sprawling city of 400 billion stars. We've looked beyond, to our neighbor Andromeda, and to the countless other island universes scattered across the void. And in this grand cosmic census, we thought we had a pretty good grasp on the scale of things. A sense of the upper limits. We felt we understood the kinds of objects that could populate the darkness between the stars. We were wrong. Deeply, fundamentally wrong. Hiding in plain sight for decades, in the farthest reaches of the distant universe, is a single object so vast, so massive, that it makes entire galaxies look small. An object that, according to everything we thought we knew about the cosmos, shouldn't exist. And yet, there it is. It's a thing of such impossible proportions that it forces us to question the very laws of physics. We've spent centuries cataloging the heavens, but we were completely blind to the true titans lurking in the abyss. We have found the real monster of the universe. And this is its story. The nature of the beast. Before we go hunting for this cosmic behemoth, we need to understand the creature we're after. We need to talk about black holes. The name itself conjures images of cosmic vacuum cleaners or violent whirlpools in space. But the reality is both simpler and way more profound. A black hole isn't a hole at all. It's not empty. Quite the opposite, it's an unimaginable amount of stuff, of mass, crushed into an impossibly small space. It's what happens when gravity, the most familiar force in the universe, wins its final, ultimate victory over everything else. Everything with mass has gravity. To escape that gravity, you need to hit a certain speed and escape velocity. For Earth, that's about 11 kilometers per second. For our Sun, it's over 600 kilometers per second. Now, just imagine an object so massive and so dense that its escape velocity is faster than the speed of light. Since nothing can travel faster than light, nothing gets out. Not a spaceship, not a planet. Not even light itself. That's a black hole. Its surface. That point of no return is called the event horizon. It's not a physical wall you could touch. It's a boundary defined by pure physics. Crossing it is a one-way trip. Once you're in, the only way to go is inward, toward the center, where all that mass is crushed into a point of infinite density, the singularity. And right there, our understanding of space, time, and reality just completely breaks down. For decades, we thought these things came in two main sizes. First, you have your stellar mass black holes. They're the ghosts of giant stars, maybe a few dozen times the mass of our Sun, scattered through galaxies like cosmic tombstones. And then you have the supermassive black holes. These are the giants that sit at the heart of almost every big galaxy, including ours. At the center of our Milky Way, 26,000 light-years away, is Sagittarius A. It's a monster, weighing in at 4 million suns. For a long time, we thought that was a titan. We could see its power in the frantic orbits of stars whipping around it. Then, in 2019, humanity did the impossible. The Event Horizon Telescope, a network of radio dishes spanning the entire globe, took the first ever direct picture of a black hole's shadow. It was the supermassive black hole in the galaxy M87. This beast tipped the scales at a staggering 4 billion solar masses. We thought we had found the heavyweights of the cosmos. Billion solar mass titans. Surely, that was as big as they could get. But the universe had a secret that would shatter our sense of scale and force us to confront a new class of object entirely. An ultramassive black hole. The clue in the catalog. Our story doesn't start with supercomputers, but in a quieter, more analog time. The year is 1957. At the Tonantzintla Observatory in Mexico, astronomers Braulio Iriarte and Enrique Chavira are photographing the sky, hunting for faint blue stars. Working through the night, they expose photographic plates, capturing tiny pinpricks of light from the deep universe. On one of these plates, they spot something. To them, it looks like just another faint star, but it has a strange quality. A distinct color. In their log, they describe it as decidedly violet. They catalog it with the number 618. And just like that, the object was born into astronomical records as ton 618. For years, that's all it was. A number in a book. A faint, weirdly colored star. The astronomers had no idea what they'd actually found. The technology to understand it didn't even exist yet. Then came the 1960s, and with them, a huge astronomical mystery. Astronomers started finding powerful sources of radio waves coming from spots in the sky that looked like faint, boring stars. They called them quasi-stellar radio sources, or quasars, for short. These things were a puzzle. Their light, when broken down into a spectrum, showed patterns that made no sense. They didn't match any known elements. The breakthrough came in 1963, when an astronomer named Martin Schmidt had a realization. The pattern wasn't alien, it was just hydrogen. But it had been stretched, distorted by an extreme redshift. Redshift is the Doppler effect for light. As an ambulance siren sounds lower when it moves away from you, light from a receding object gets stretched toward the red end of the spectrum. And thanks to Hubble's law, we know that the more redshifted something is, the faster it's moving away from us and the farther away it is. Schmidt's discovery was earth-shattering. The massive redshifts of these quasars meant they weren't stars in our galaxy. They were billions of light-years away. And if they were that far away and still bright enough to see, their true power had to be unbelievable. A single quasar had to be shining with the light of hundreds of galaxies. What kind of engine could do that? In 1970, the mystery of Ton 618, our faint violet star, started to unravel. A radio survey in Italy picked up radio waves coming from its exact position. Suddenly, it was a quasar. Intrigued, another astronomer, Marie Helena Ulrich, pointed a powerful telescope at it and got a detailed spectrum. It was confirmed. The spectrum showed the classic, massively redshifted lines of a quasar. From that redshift, she calculated its distance, an incredible 10 billion light-years from Earth. That unassuming dot from 1957 was actually one of the most luminous objects ever discovered. The clue had been sitting there for 13 years, a cosmic monster disguised as a firefly. But the light wasn't the monster. The light was just the symptom. The true beast was the engine powering it all, hidden deep inside the fire. The engine of impossible brilliance. To understand the Leviathan that is Ton 618, you have to understand the incandescent cloak it wears. A quasar's light is one of the most extreme things in the universe, a beacon so powerful it completely outshines the galaxy it lives in. But this light doesn't come from the black hole itself. They are, by definition, black. This brilliance is the death scream of matter. Picture a supermassive black hole at the center of a young, gas-rich galaxy. Its gravity is an inescapable vortex in space-time. Gas, dust, even entire stars get captured and begin a final, desperate spiral inwards. This material doesn't fall straight in. It flattens into a vast, spinning plate of matter called an accretion disk. This is the engine of the quasar. The accretion disk around Ton 618 is a place of almost unimaginable violence. As countless stars and gas clouds get pulled in, they're accelerated to nearly the speed of light. The friction and pressure are so intense that the matter is heated to millions of degrees, torn apart at the atomic level into a seething plasma that unleashes a torrent of energy. It's hard to describe how bright this is. The quasar powered by Ton 618 shines with the light of 140 trillion suns. Let that number sink in. 140 trillion. If our sun were a single grain of sand, the light from this one quasar would be a mountain of sand weighing over 60,000 tons. It's more luminous than all the stars in the Milky Way and Andromeda galaxies combined, and then multiplied by 1,000. It's a floodlight so powerful you could see it from the edge of the observable universe. This is the source of that, decidedly violet, light seen back in 1957. The disk is so hot, it glows brightest in ultraviolet. But because it's so far away, the expansion of the universe stretched that UV light all the way into the visible spectrum, giving it that distinct color. Astronomers realized that for a disk to shine that brightly, the monster at its heart had to be eating an enormous amount of matter. The brightness was a direct clue to how voracious it was. By analyzing the light, they could figure out how fast the gas in the disk was moving, and from that, they could do a cosmic calculation. They could weigh the unseen object at the center. They were about to put the true monster on the scales. And the number that came back was, and still is, unbelievable. Weighing a Leviathan. Let's recalibrate our sense of scale one more time. Our galaxy's black hole, Sagittarius A*, is 4 million solar masses. The famous M87 black hole, the first one we ever photographed, is over 1,000 times bigger, at 5.4 billion solar masses. For a while, it was the undisputed champion. The mass calculated for the black hole at the heart of Ton 618 is 66 billion times the mass of our Sun. 66 billion. It's a number that almost loses its meaning. It's over 15,000 times more massive than our own galaxy's central black hole. It's more than 10 times the mass of the celebrity black hole in M87. In fact, this single object is more massive than all 400 billion stars in our entire Milky Way galaxy combined. All of it. All the stars, gas, and dust of our home galaxy would not even tip the scales against this one solitary object. It belongs to a whole new category: the ultramassive black holes. This mind-boggling mass has a direct physical consequence: its size. The diameter of Ton 618's event horizon is roughly 390 billion kilometers. That's 600 times the distance from the Earth to the Sun. To put that in perspective, let's imagine dropping this thing into the center of our solar system. The Sun would be gone instantly. The Earth would vanish. Jupiter, deep inside the abyss. Let's go further out. The orbit of Neptune, our most distant planet, is about 30 astronomical units from the Sun. You could fit the entire orbit of Neptune across the face of this black hole more than 80 times. The Voyager 1 probe, humanity's most distant creation, has been traveling for nearly 50 years. It would have barely crossed 6% of the distance of the event horizon. Think of it in terms of light. It takes about 8 minutes for light to get from the Sun to the Earth. To cross the event horizon of Ton 618 from one side to the other, a beam of light would need over 15 days. A week and a half just to cross the point of no return. We're talking about a circle of pure blackness in the sky so big that our entire solar system becomes an irrelevant speck of dust. This is the true monster. Not of teeth and claws, but of gravity and space-time. A sphere of absolute nothingness larger than dozens of solar systems, holding the mass of an entire galaxy. And maybe the most terrifying fact isn't its size, but its age. The impossible youth. The light from Ton 618 has been traveling for about 10.8 billion years to reach us. That means we're seeing it as it was when the universe was just 3 billion years old, a mere toddler in cosmic terms. And this presents a profound, universe-altering paradox. How did it get so big, so fast? Our current theories of how black holes grow just can't explain Ton 618. There hasn't been enough time. In the early universe, there wasn't enough time for a regular black hole to form from a star and then eat its way up to 66 billion solar masses. It's like a baby growing to the size of a blue whale in a few minutes. The existence of an object like this so early in cosmic history tells us our understanding of the universe might be incomplete. It suggests there have to be faster ways to make monsters. One leading idea is direct collapse black holes, where an enormous, primordial cloud of gas in the early universe, hundreds of thousands of times the mass of the Sun, could collapse all at once, skipping the star phase and forming a massive black hole. Seed. Right from the start. Another possibility is that Ton 618 just found itself in a perfect cosmic storm born in an incredibly dense part of the universe where it was force-fed a constant, high-speed river of gas, allowing it to grow at a shocking rate. We don't have the final answer. Ton 618 isn't just a record holder, it's an anomaly. It's a piece of evidence telling us our story of the universe is missing a chapter. It's a beautiful, terrifying wrench in the gears of our cosmic clockwork. It forces us to ask, if this could form so early on, what else is out there, lurking in the dark? How many more of these ultramassive entities are out there, their quasar engines now silent, leaving them completely invisible to us? A reflection in the abyss. We started this journey in our familiar cosmic neighborhood, and we've traveled across space and time to the very edge of comprehension. We have stood at the brink of a void 600 times wider than the Earth's orbit, an object holding the mass of a galaxy, shining with the light of 140 trillion suns. TON 618 is a profound lesson in humility. For centuries, we've tended to place ourselves at the center of things. First, we thought the universe revolved around Earth. Then, our sun. Then, our galaxy. And each time, a discovery came along that pushed us further from the center, reminding us that we live on an ordinary planet, orbiting an ordinary star, in an ordinary galaxy. TON 618 is the ultimate expression of this idea. It shows us that the scales of mass and energy we're used to, even the scale of our entire galaxy, are trivial on the grandest stage. But there's another side to this story. The fact that we from our tiny world can even know that such an object exists is a testament to the power of human curiosity. We are the part of the universe that has woken up and is trying to piece together its own story. The same laws of physics that allow for TON 618 to exist also gave rise to the minds that can measure it, comprehend it, and be struck with awe by it. The monster isn't evil. It's a natural, if extreme, part of the cosmic ecosystem. And finding it doesn't make our existence less meaningful. It makes the universe infinitely more interesting. It reminds us that for all we've learned, we have barely scratched the surface. The darkness is filled with wonders we can't even imagine yet, and our journey into it has only just begun. The hunt for monsters continues. If you've ever felt small looking up at the night sky, now you have a new reason why. And if that feeling of awe and curiosity is something you want more of, consider subscribing. The universe is waiting. The universe's cannibal monster factory. In the dead center of a galaxy far, far away, there's a monster. It's a black hole, but not just any black hole. This one, named TON 618, is so incomprehensibly massive it makes our sun look like a single grain of sand next to a mountain. Recent estimates put its weight at a mind-bending 40 billion times the mass of our star, though some calculations go as high as 66 billion. If you were to place it in the center of our solar system, its shadow, its zone of inescapable darkness, wouldn't just swallow Earth, or Jupiter, or even Neptune. It would stretch out past the Voyager probes, past the boundaries of our solar system, and deep into interstellar space. These things, these supermassive black holes, are the titans of the cosmos. They are the heaviest individual objects in existence. And the most terrifying part? They weren't born this way. They were built. This is the story of how the universe manufactures its monsters, a 13.8 billion-year tale of cosmic violence, relentless cannibalism, and galaxy-devouring titans. Almost every large galaxy, including our own Milky Way, has one of these leviathans lurking in its core. They are the gravitational anchors, the puppet masters dictating the motions of hundreds of billions of stars. Yet, their very existence presents a profound cosmic puzzle. We see them fully formed, weighing billions of suns, in the absolute infancy of the universe, less than a billion years after the Big Bang. That shouldn't be possible. It's like finding a fully grown redwood tree that's only 1 year old. It defies the known rules of growth. Somehow, these black holes grew faster and more violently than we can easily explain. They didn't just sip matter from the cosmos. They gorged themselves in a feeding frenzy that lasted for eons. The story of their growth is not one of quiet, steady accumulation. It's a brutal epic written in the language of shredded stars, colliding galaxies, and gravitational chaos. So, how did they do it? How do you build a monster that can outweigh an entire galaxy's worth of stars? To understand the factory, we first need to appreciate the terrifying scale of its products. Then, we'll retrace the manufacturing process, from the first seeds of destruction to the final, galaxy-ruling titans. We'll uncover the 3 brutal methods they use to grow: a relentless consumption of cosmic gas, violent collisions with their own kind, and the grand, destructive dance of galactic mergers that fuels their insatiable appetite. The scale of the monsters. Before we can get into how these cosmic behemoths are made, we need to recalibrate our sense of scale. The numbers are so astronomical they can feel meaningless, so let's try to build a mental picture of just how profoundly large these objects are. Let's start at home, in our cosmic backyard. At the heart of the Milky Way, 26,000 light-years away, lies Sagittarius A *, our galaxy's supermassive black hole. It sounds impressive, and it is, weighing in at about 3 million times the mass of our Sun. Its event horizon, the gravitational point of no return, would fit comfortably inside the orbit of Mercury. It's a giant by human standards, but in the grand cosmic zoo, it's a relatively modest creature. Now, let's take a step up. Travel 55 million light-years to the Virgo galaxy cluster, and you'll find Messier 87, or M87. This is the galaxy that is home to the first black hole we ever directly photographed. The black hole at its center, M87*, is a true monster, weighing around 6.5 billion times the mass of our Sun. Our Sagittarius A is a kitten by comparison. The shadow of M87 is so vast that a beam of light, the fastest thing in the universe, would take 2.5 days to travel across it. Think about that. Light can circle the Earth 7.5 times in a single second, yet it would take days just to cross the shadow of this one object. Our entire solar system would be like a tiny marble rolling around inside it. But the universe has factories that build even bigger. Much bigger. In a galaxy cluster in the constellation Coma Berenices lies NGC 4889, home to a black hole estimated to weigh around 21 billion solar masses. Its event horizon is so large that it would swallow the orbits of all our planets, reaching far out into the icy Kuiper belt where Pluto resides. And then, we come back to the champion, the king of the cosmic monsters, Ton 618. This object is technically a quasar, meaning we're seeing the brilliant, blinding light of matter being actively consumed by its central black hole. The light from Ton 618 has been traveling for over 10 billion years to reach us, meaning we're looking at it when the universe was still in its youth. The black hole powering this quasar has a currently accepted mass of around 40 billion suns, with some earlier estimates placing it as high as 66 billion. The event horizon of Ton 618 has a radius of about 1/300 times the distance from the Earth to the Sun. If it sat where our Sun is, its gravitational edge would swallow every planet, asteroid, and comet, continuing out past the Voyager probes and deep into interstellar space. The shadow it casts is so enormous that you could line up our solar system, out to Neptune, over 40 times, edge to edge, and they would all fit inside. For a long time, theorists figured there was a practical upper limit to how large a black hole could grow, somewhere around 50 billion solar masses, because beyond that, the accretion disk itself should become unstable and start forming stars instead of feeding the black hole. But monsters like Ton 618 are pushing, and perhaps even breaking, that theoretical boundary, suggesting they must be spinning incredibly fast to remain stable. Now, it's important to maintain perspective. As vast as these black holes are, their host galaxies are orders of magnitude larger. But it's a very, very influential speck of dust. Its gravity governs the orbits of the innermost stars, and the energy it releases when it feeds can influence star formation throughout the galaxy. In fact, new research suggests that the most powerful quasars can emit so much radiation they can suppress star formation not just in their own galaxy, but in neighboring galaxies millions of light years away, effectively sterilizing their cosmic neighborhood. So when we talk about these monsters, we're talking about objects with the mass of billions of stars compressed into a volume smaller than our solar system. We're talking about gravitational fields that hold entire galaxies in their sway. They are the universe's heavyweights, the final word in cosmic density. And every single one of them started small. The seeds of destruction. Every monster has an origin story. For supermassive black holes, that story begins with a seed. Before you can get a titan weighing billions of suns, you need a gravitational anchor to start the process. The universe, in its earliest days, was a frantic and violent place, and it offered two primary ways of creating these black hole seeds. The debate over which path was more important is one of the hottest topics in cosmology today. The first, more straightforward method is the stellar seed model. This starts with the very first stars, known as population 3 stars. These weren't like the stars we see today. Born from pure hydrogen and helium left over from the Big Bang, they were gigantic hundreds, maybe even 1,000 times the mass of our Sun. These giants lived fast and died young, collapsing directly into black holes of a few hundred to 1,000 solar masses. In the dense cores of the first galaxies, these light seeds would have sunk to the center and merged, creating an intermediate mass black hole of maybe 10,000 solar masses. A decent starting point. But here's the problem. We see quasars powered by billion solar mass black holes when the universe was less than a billion years old. Growing from a 10,000 solar mass seed that quickly is a huge challenge. It's like trying to fill an Olympic-sized swimming pool with a garden hose in under an hour. This is where the second theory comes in. The heavy seed, or direct collapse, model. This scenario skips the star part entirely. Under very specific conditions, a gigantic cloud of primordial gas weighing as much as 100,000 suns could have been hit with intense ultraviolet radiation from a nearby galaxy. This radiation would prevent the cloud from breaking up and forming stars. Instead, the entire cloud collapses catastrophically under its own gravity, forging a heavy seed, a black hole born with a starting mass of 10,000 to 100,000 solar masses. Starting with a heavy seed is like starting with a half-full swimming pool. It makes the problem of those early, giant quasars much more manageable. And recent discoveries from the James Webb Space Telescope, JWST, have found compelling candidates that seem to fit this profile. For example, astronomers have found systems where massive black holes appear to be forming in the chaotic, gas-rich space between two colliding galaxies, a perfect scenario for this kind of formation. Another object, a quasar named UHZ-1, seen when the universe was just 470 million years old, is so massive for its age that it serves as powerful evidence for the heavy seed model. So the universe had two factory lines for its monster seeds. One, a common assembly line, taking the corpses of the first giant stars and smashing them together. The other, a specialized production line, using a rare cosmic alignment to forge massive seeds from scratch. It's likely both processes were at play. But a seed is just a seed. The next step is where the real growth happens. The next step is the feast. The primary growth engine. Cannibalizing gas. A seed black hole, even a heavy one of 100,000 solar masses, is a long way from the billion solar mass monsters we see dominating early galaxies. To bridge that gap, a black hole needs to eat. And its primary food source, the fuel that powers the vast majority of its growth, is gas. This process, called accretion, is the true engine of the cannibal factory. Imagine a seed black hole in the center of a young galaxy, surrounded by vast clouds of cold hydrogen gas. The black hole's gravity pulls this gas toward it, but the gas doesn't fall straight in. It has some sideways motion, so it gets whipped into a flattened, spinning structure called an accretion disk. And this is where the real action happens. The accretion disk is a maelstrom of violence. Gas spirals inward at incredible speeds, approaching the speed of light. Friction between different layers of gas generates a staggering amount of heat, causing the disk to glow with an intensity that can outshine all the billions of stars in its host galaxy combined. This is what we see as a quasar. A quasar isn't the black hole itself that's invisible. It's the death scream of matter in the accretion disk, superheated to brilliance just before it takes the final plunge. This process is fantastically efficient at converting mass into energy, far more so than the nuclear fusion that powers stars. However, this very efficiency creates a natural speed limit, known as the Eddington limit. The intense light blasting out from the hot disk exerts an outward pressure. If a black hole tries to eat too fast, the sheer brightness of its own meal pushes away more incoming gas. It's a self-regulating loop. Eat more, shine brighter, push food away, eat less. For years, this was a huge problem for explaining the early giants. If black holes were bound by this limit, they just couldn't shovel in the gas fast enough. So, how did they break the speed limit? It turns out the universe has tricks for super Eddington accretion. If the gas is clumpy, dense filaments can punch through the radiation pressure like bullets through a strong wind. Even better, when accretion rates get really extreme, the disk can puff up into a thick, bloated donut. In this slim disk shape, much of the radiation gets trapped inside the gas and carried into the black hole instead of escaping. This muffles the push back, allowing the black hole to guzzle gas at rates hundreds of times the normal limit, especially during an era called cosmic noon, about 2 to 3 billion years after the Big Bang, when galaxies were gas-rich and constantly crashing into each other. So the primary weapon is a sustained, often supercharged, assault of gas flowing into the black hole's maw, lighting up the cosmos as a brilliant quasar. This process built the bulk of their mass. But it didn't happen in a vacuum. The universe had to deliver this gas through incredible violence. Before we get to that cosmic demolition derby, if you're enjoying this deep dive into the universe's most extreme creations, take a moment to subscribe. Your support lets us explore these cosmic mysteries together. The tag team. Black hole mergers. While the relentless consumption of gas is how supermassive black holes pack on most of their mass, it isn't their only tool. There's another, more direct and arguably more violent method of growth: merging with other black holes. If gas accretion is a long feast, a black hole merger is a single, cataclysmic gulp that can add millions or billions of solar masses in an instant. This is an inevitable consequence of how galaxies evolve. Over cosmic time, galaxies collide and merge. And since almost every large galaxy has a supermassive black hole, when two galaxies merge, their central black holes are set on an unavoidable collision course. As the two galaxies dance around each other and combine, the two black holes sink toward the new center. Eventually, they find each other and form a binary pair, orbiting their common center of mass. As they get closer, they begin to radiate away energy in the form of gravitational waves, ripples in the fabric of spacetime itself. This energy loss causes their orbit to shrink, faster and faster, in a death spiral from which there is no escape. In the final moments, they're whipping around each other at a huge fraction of the speed of light. Finally, they touch. The two event horizons become one, creating a single, larger black hole that violently rings like a struck bell, emitting a final, powerful burst of gravitational waves before settling down. We can see this process in action. The galaxy NGC 7727, about 89 million light-years away, contains two supermassive black holes at its core, the leftovers of a merger that happened about 1 billion years ago. The larger one weighs 154 million solar masses, while its partner is about 3 million. They're currently separated by 600 light-years and are expected to merge in about 250 million years, creating a single black hole of over 160 million solar masses. So how important are these mergers? Studies show that while they're significant, they are a secondary channel compared to gas accretion. For most black holes, especially in the early universe, gas was the main course. Mergers were more like a substantial dessert. Their importance grows over time, though. In the last 7 billion years, as the universe's gas supply has dwindled, mergers have become a more critical path for growth, especially for the biggest black holes in giant elliptical galaxies. The ultimate feeder. Galaxy collisions. We've got the two direct methods for growth: the steady engine of gas accretion and the jolts from black hole mergers. But neither happens in isolation. They both need a catalyst, a mechanism that delivers the fuel. That mechanism is the galaxy collision. Galaxy mergers are the ultimate feeder system for the cannibal factory. Imagine a stable galaxy like our Milky Way. Most of its gas is peacefully orbiting in the disk, and our central black hole, Sagittarius A*, is mostly dormant. To make it feast, you have to shake the cosmic snow globe. And nothing does that better than smashing another galaxy into it. When two galaxies collide, their stars mostly pass by each other like ghosts. But their huge clouds of gas slam into each other with tremendous force. The gravitational chaos of the merger robs the gas of its momentum, preventing it from staying in a stable orbit and funneling it directly toward the center of the newly forming galaxy. This sudden, massive influx of gas has two dramatic consequences. First, it triggers a starburst, forming new stars at a furious rate. Second, and most important for our story, this deluge of gas provides an all-you-can-eat buffet for the supermassive black holes. The gas forms a massive accretion disk, triggering a luminous quasar phase and the rapid, super-Eddington growth we talked about. In this sense, a galaxy merger is the ultimate enabler. It's the delivery mechanism that transports fuel from the galactic suburbs to the hungry monster downtown. This explains why quasars were so much more common in the early universe. That chaotic era was the golden age of galactic mergers, providing a steady supply of gas to their central black holes and allowing them to grow exponentially. Today, in our more spread-out universe, major mergers are less common, but we still see their effects. Many of the most active galaxies nearby show telltale signs of a recent collision. The connection is clear. If you want to feed a supermassive black hole, crashing its galaxy is the most effective way to do it. The cosmic timeline. So let's assemble the factory's components along the 8 billion year timeline of the universe. Our story begins in the cosmic dark ages, just a few 100 million years after the Big Bang. The first giant stars ignite, live their short, furious lives, and die, leaving behind stellar mass black hole seeds. In rarer environments, direct collapse creates heavy seeds up to 100,000 solar masses. This all happens by the time the universe is about 250 million years old. Now, the factory kicks into high gear. This is the epoch of reionization, a time of cosmic chaos. Protogalaxies are constantly smashing together. Every merger funnels a firehose of gas toward the central seed black hole. This triggers the first great growth phase, with seeds accreting matter at furious, super-Eddington rates. This is how we get billion solar mass black holes when the universe was only 700 million years old. The combination of heavy seeds and merger-driven hyperaccretion is the only mechanism that seems to fit. As we move into cosmic noon, from 1 to 3 billion years after the Big Bang, the process continues. This is the peak era for both star formation and quasar activity. By the end of this epoch, the bulk of the mass for most supermassive black holes is already in place. The monsters we see today were mostly built by this point. From about 3 billion years after the Big Bang onward, the universe starts to change. It's expanding, galaxies are getting farther apart, and the gas supply is dwindling. The great feasts are ending. Gas accretion slows to a trickle, and many black holes, like Sagittarius A*, enter a long period of dormancy. In this later epoch, from about 7 billion years ago to today, the main driver of growth for the most massive black holes shifts from accretion to mergers. Giant elliptical galaxies, themselves the product of many past collisions, sit at the center of galaxy clusters, and with each galaxy they swallow, their central black hole gets a chance to merge and grow larger. While accretion built the monsters, mergers are what allow the Goliaths to continue their reign. From a single seed to a cosmic titan weighing 40 billion suns. The journey of a supermassive black hole is one of the most extreme stories of growth the universe can tell. They weren't born as monsters. They were meticulously, violently, and relentlessly built over billions of years in the universe's great cannibal factory. We've seen that it's a three-part process. It starts with a seed, the remnant of a colossal first star, or the direct collapse of a giant gas cloud. Then comes the Great Feast. A relentless torrent of gas, funneled into a brilliant accretion disk that can outshine galaxies. And driving it all is the destructive ballet of galaxy collisions, the cosmic delivery service that smashes galaxies together, unleashes rivers of fuel, and brings black holes together for the final, universe-shaking merger. The timeline of this growth mirrors the universe's own evolution. A frantic beginning in a dense, violent cosmos, followed by a slower consolidation in a mature, expanding universe. The titans we see today, like M87* and Ton 618, are not just objects, they're fossils. They're living records of a more brutal and chaotic cosmic past. They are the universe's apex predators, the gravitational anchors around which galaxies are built. Their growth shapes the evolution of everything around them. The next time you look up at the serene band of the Milky Way, remember the 4 million solar mass monster sleeping at its heart. Remember that its quiet slumber was earned through an eon of unimaginable violence. It is a retired cannibal, a sleeping giant, built in the universe's most formidable factory. Black holes are secretly building the universe. We've all been told a lie about black holes. That they're the universe's ultimate destroyers, just cosmic vacuum cleaners endlessly gobbling up everything in their path. A one-way ticket to nothingness. The end. But what if that's only half the story? What if the most destructive things in the cosmos are also the universe's greatest builders? We now have real evidence that black holes are the secret architects of the universe, deciding where and when whole generations of stars are born. This isn't science fiction. This is a revolution in how we see the universe, and it flips the script on everything we thought we knew about these cosmic monsters. The myth of the cosmic vacuum cleaner. For decades, the image of the black hole has been seared into our minds as a purely evil force. A bottomless pit that not even light can escape. We've seen the animations of stars getting stretched into spaghetti, of planets being swallowed whole. The story is simple and terrifying. Black holes are the universe's apex predators, agents of pure chaos. When something falls in, its story is over. It's wiped from the cosmic ledger, locked away forever. This idea is so powerful because it taps into a primal fear of the unknown. And let's be fair, it's not totally wrong. Black holes are masters of consumption. Their gravity is the most extreme force we know. But just calling them destroyers is to miss the profound, almost beautiful truth of what they are. It's like looking at a volcano and only seeing the destructive lava, while ignoring the fact that its ash creates some of the most fertile soil on the planet. The cosmic vacuum cleaner is a myth, a massive oversimplification. Because in reality, black holes are messy eaters. In fact, they're terrible eaters. And in that spectacular, galaxy-spanning mess they make when they feed, they seed the entire universe with the exact conditions needed for creation. They aren't just the end, they're also a new beginning. And figuring out this double life is the key to solving one of the biggest puzzles in all of cosmology. The cosmic problem. An unbalanced universe. To get why black holes have to be more than destroyers, you first need to understand a huge problem that stumped astronomers for decades: the mystery of the quenched galaxy. Think of a galaxy as a giant city of stars. In the early universe, these cities were booming. They were packed with enormous clouds of cold gas, the raw material for making new stars. Like out-of-control construction zones, these young galaxies were cranking out stars at unbelievable rates. Based on our simplest models, that star-making party should have just kept going. Galaxies should have kept pulling in gas, getting bigger and bigger, their star factories working overtime until all the fuel was used up. We should see galaxies today that are absolutely stuffed with stars way more than they actually have. But that's not what we see. When we look out at the cosmos, we see that something slammed on the brakes. Around 11 billion years ago, the universe-wide pace of star formation started to plummet, dropping to a rate 30 times slower than its peak. Many of the most massive galaxies, the ones that should have been the most productive, look like they just quit. They're now filled with old, red, dying stars, and their star-making nurseries have all gone quiet. They're quenched. This was a huge headache for astrophysicists. What could possibly operate on a galactic scale to shut down star formation? What force is strong enough to sterilize an entire galaxy to heat up or blow away trillions of suns worth of star-making gas across hundreds of thousands of light years? There had to be some kind of cosmic thermostat, a self-regulation system that stops galaxies from overheating with too many stars. For a long time, we had suspects, but no smoking gun. Supernova explosions from dying stars can blow some gas around, but not nearly enough to shut down a whole galaxy. The answer had to be way more powerful, something located right at the heart of the action, capable of projecting its influence across the entire system. The main suspect was the supermassive black hole hiding at the galaxy's core, but how it worked was a total mystery. How could an object whose whole deal is pulling things in be responsible for pushing things out on such a mind-boggling scale? The answer, it turns out, isn't in the black hole itself, but in the violent, chaotic way it eats. The revelation. The messy eater. So, let's update our image of a black hole. Forget the tidy vacuum cleaner. Instead, picture a supermassive black hole like a giant baby in a high chair, being fed way more food than it can handle. The result isn't a clean plate, it's a complete disaster. Food gets flung everywhere. When huge amounts of gas and dust spiral toward the central black hole, they don't just fall straight in. They form a massive, swirling structure called an accretion disk. This is where things get crazy. Think of the disk as a traffic jam of matter on a cosmic highway, all trying to merge into the single lane of the black hole's event horizon. As this stuff gets closer, it orbits at insane speeds, and the friction from all that material rubbing together heats it up to millions of degrees. The disk becomes a blazing furnace, shining brighter than all the billions of stars in its galaxy combined. This is what we call a quasar, or an active galactic nucleus. AGN. The luminous, angry scream of a black hole having a feast. This whole process is unbelievably inefficient. While a lot of stuff does end up falling into the black hole, a huge portion gets violently thrown back out. The intense heat and pressure at the center of the disk, combined with the black hole's powerful, twisted magnetic fields, act like a cosmic slingshot. They grab a fraction of the incoming material and launch it outwards in two colossal, opposing beams of particles rocketing out at nearly the speed of light. These are called relativistic jets. These jets are some of the most powerful events in the entire universe. They can blast out of the galaxy's core and travel for millions of light years, far beyond the visible edge of the galaxy itself. At the same time, the blinding light from the quasar acts like a powerful hurricane of energy, pushing on all the surrounding gas. This whole process, the launching of jets and the blast of radiation, is what scientists call black hole feedback. It's the black hole pushing back against the very galaxy that feeds it. It's the messy eater flinging food across the room. And it's this violent, powerful feedback that holds the secret to both destroying and creating on a galactic scale. It's the solution to the mystery of the quenched galaxies and the key to the black hole's role as a master builder. Sizing up the architects, a matter of scale. To really feel the power of black hole feedback, we need to completely reset our sense of scale. The word, supermassive, just doesn't do these things justice. They are so ridiculously big and dense that our minds can barely even process it. So let's try. We'll start with a relative lightweight. In the dwarf galaxy 1601 plus 3113, there's a supermassive black hole with the mass of 100,000 suns. But because all that matter is crushed into a single point, its shadow, the dark zone created by its gravity-bending light, is actually smaller than our own sun. Now, let's come home to our Milky Way. At its heart, 26,000 light-years away, sits Sagittarius A. By watching stars whip around it, we've pinned its mass at a hefty 3 million times that of our Sun. Its shadow covers an area about half the size of Mercury's orbit. But honestly, Sagittarius A is a cosmic kitten. Let's hop over to Andromeda, our nearest big galactic neighbor. Its central black hole weighs in at around 140 million solar masses. Now we're talking. Let's visit the galaxy NGC 7727. Astronomers there found two supermassive black holes spiraling toward a merger. One is 6 million solar masses, but its partner is a monster of over 150 million suns. The shadow of that bigger one would easily swallow the orbits of Earth and Mars. Next up, the famous M87 galaxy. This was the target of the very first picture ever taken of a black hole, an icon of modern science. M87's central beast has a mass of about 6.5 billion suns. Its event horizon is so big that light, the fastest thing there is, would take 2.5 days to cross it. Our entire solar system, all the way out to Pluto, would be just a tiny speck inside this circle of darkness. But we can go bigger. Much bigger. We're now entering the realm of ultramassive black holes. In the galaxy Cygnus A, there's a black hole of 2.5 billion suns. It's eating so much that it shoots out jets that create enormous radio-emitting lobes that tower over the galaxy, stretching 500,000 light-years from end to end. The black hole in the galaxy cluster NGC 4889 is even more of a monster, at 21 billion solar masses. And finally, we arrive at the current king, the undisputed heavyweight champion of the known universe, Ton 618. This object is a hyperluminous quasar, so far away we're seeing it as it was over 10 billion years ago. The black hole powering it is almost impossible to comprehend. An estimated 66 billion times the mass of our Sun. This one object is more massive than many entire galaxies. Its event horizon is so vast it would take light weeks to cross it. If you placed it in our solar system, it wouldn't just swallow all the planets. Its edge would stretch past the Voyager probes and deep into the Oort cloud. You could line up 11 of our solar systems side by side inside of it. These aren't just points of insane gravity. They're the gravitational anchors of the cosmos. And their size isn't random, it's directly linked to the size of the galaxy they live in. This deep connection, called co-evolution, is the biggest clue we have that these giants are not just passive tenants. They are colossal architects whose sheer scale gives them the power to decide the fate of the trillions of stars around them. The two faces of feedback. Negative feedback, the cosmic pruner. Okay, now that we have a sense of the insane scale of these architects, we can understand the power of their feedback. This feedback has two main modes, one that stops creation and one that starts it. First, let's look at the negative feedback side. Think of it as the black hole acting like a cosmic pruner. This is the most direct result of a black hole's messy eating. When a supermassive black hole flares up as a quasar, the energy it blasts out is just incredible. The radiation from the accretion disk creates a powerful, galaxy-scale wind that rips through the entire galaxy. This wind acts like a superheated blowtorch, heating up the vast clouds of cold gas that stars are made from. And that's the key. Stars are born from cold, dense gas. Gravity needs to be able to pull that gas together into clumps that can collapse and ignite. But if you heat the gas up, its atoms start zipping around too fast, creating an outward pressure that fights against gravity. The gas cloud can't collapse anymore. It becomes sterile, unable to form new stars. That quasar wind effectively shuts down a galaxy's star-making factories. Recent studies even show this can affect neighboring galaxies, with the light from one powerful quasar stopping star formation millions of light years away. Then you have the jets. These focused beams of plasma are even more powerful. They punch clean through the galaxy, carving out enormous cavities that can be hundreds of thousands of light years wide. As they slam into gas clouds, they create powerful shockwaves that heat the gas to millions of degrees, making it totally useless for star formation. Sometimes, the jets are so strong they just blow the gas right out of the galaxy, ejecting it into deep space where it can't be used as fuel. We see the evidence for this everywhere. Astronomers look at those massive, quenched galaxies and find they're filled with incredibly hot, thin gas, but have almost no cold gas for star making. And right at their centers? They always have gigantic supermassive black holes. The story writes itself. These galaxies and their black holes grew up together. Eventually, the black hole got so big and its feeding so intense that it flipped a switch. Its winds and jets turned on, heating and blasting away the galaxy's remaining fuel. This creates a self-regulating loop. If there's lots of cold gas, the black hole eats, its feedback gets powerful, and it gets rid of the gas. Once its food supply is gone, the black hole quiets down, the quasar fades, and the jets die out. The galaxy is now quenched. Over huge amounts of time, gas might cool down or drift in from outside, maybe starting the whole cycle over again. This negative feedback is the answer to the mystery of the quenched galaxies. It's a cosmic thermostat. The black hole acts like a pruner, trimming the galaxy's star-forming branches and shaping it into its final, stable form. It's not destroying the galaxy, it's regulating it. This is the first huge piece of the puzzle, showing the black hole as an architect that decides not just where stars are born, but more importantly, where they are not. The two faces of feedback. Positive feedback, the cosmic gardener. If negative feedback is the black hole as a stern regulator, then positive feedback is its creative, nurturing side. It's the shocking, Counterintuitive discovery that the same violent outflows that can shut down a galaxy can also, in the right situation, trigger brilliant bursts of new stars. This is where the black hole really becomes a builder. Think about those colossal jets blasting from the galactic center again. We've seen how they can heat gas up. But what if, instead of hitting a thin, diffuse cloud, the jet slams into a much denser, clumpier patch of gas? The result isn't just heating, it's also compression. Imagine a cosmic snowplow. The shockwave at the front of the jet sweeps up the surrounding gas, piling it high and squeezing it to incredible densities. This is the exact opposite of what we saw before. By crushing this gas together, the jet can push it over the critical point where gravity takes over, causing it to collapse and ignite into a whole flurry of new stars. The jet, an instrument of supposed destruction, actually becomes a trigger for creation. And we are now seeing this happen. Observations of a galaxy cluster called SDSSJ1531 show a supermassive black hole firing off a powerful jet. Along the edge of the cavity carved out by this jet, astronomers found a stunning string of beads, a chain of 19 massive young star clusters, all forming in a perfect arc. The black hole's violent outburst literally birthed an entire generation of stars. There's another, even wilder form of positive feedback. Sometimes, a runaway supermassive black hole gets kicked out of its own galaxy during a merger. As it careens through intergalactic space, its gravity creates a shockwave in front of it, compressing gas in its wake and leaving behind a trail of newborn stars, like a ship leaving a foamy trail in the ocean. The Hubble Space Telescope may have caught a jaw-dropping picture of this. A 200,000 light-year-long, perfectly straight line of brilliant blue stars, pointing directly away from a distant galaxy, a cosmic breadcrumb trail left by an invisible, runaway black hole. Even the negative feedback can have a positive twist. When a jet blows gas out of a galaxy, it doesn't always escape for good. That gas can rain back down onto the galaxy millions of years later, delivering a fresh supply of fuel for another round of star birth. The black hole acts like a galactic fountain, recycling material and ensuring the galaxy can keep building stars over cosmic time. This duality is what makes black holes so essential. They're not simple on-off switches. They are complex engines of change. The very same mechanism, energy flowing out from a feeding black hole, can have totally opposite effects depending on what it runs into. It can quench a galaxy, or it can plant the seeds for new stars. The black hole is both the pruner and the gardener, shaping the stellar landscape of its galaxy with a power we are only just beginning to understand. The evidence. How we see the invisible. This whole story might sound like a cool theory, but how do we actually know it's happening? How can we possibly watch these processes, orchestrated by invisible objects, from billions of light years away? The answer is by using an incredible array of telescopes that see the universe in ways our eyes can't, listening for the whispers and watching for the shadows that black holes leave behind. The most famous of these is the Event Horizon Telescope, or EHT. It's not one telescope but a global network of radio dishes, all working together as a single, Earth-sized observatory. This is the instrument that gave us those iconic images of the black holes in M87 and our own Sagittarius A. What you're seeing in those pictures isn't the black hole itself, but its shadow cast against the glowing hot gas of the accretion disk. By studying that shadow, scientists can measure the black hole's mass and even map the magnetic fields that launch the jets. To see the jets themselves, we use radio telescopes like the Very Large Array. Radio images reveal the colossal lobes of plasma the jets inflate, showing us the true scale of the black hole's influence. To see negative feedback in action, the hot gas, we need X-ray telescopes in space, like NASA's Chandra X-ray Observatory. Cold gas doesn't emit X-rays, but gas heated to millions of degrees glows brightly. When Chandra looks at quenched galaxies, it sees them enveloped in a vast halo of X-ray emitting gas, the smoking gun of black hole feedback. And to see positive feedback, the actual creation of stars, we now have the James Webb Space Telescope. With its incredible infrared vision, JWST can peer through the thick dust where new stars are born. It can see the delicate threads of gas being compressed by a black hole's outflow and spot the pockets of intense star birth triggered by a passing jet. JWST has also been crucial in finding supermassive black holes in the very early universe, showing they grew much faster than we ever thought possible. By combining data from all of these instruments, the EHT's shadows, the VLA's radio jets, Chandra's hot gas, and JWST's infrared starbursts, astronomers are piecing together the complete story. We're no longer guessing. We are watching the architects at work. The universe is filled with these incredible connections, where the most violent processes give rise to the most beautiful structures. The story of the black hole architect is a perfect example of how much we're still learning, and how every new discovery makes the cosmos even more fascinating than we ever imagined. If you find this new vision of the universe as breathtaking as we do, and you want to keep exploring the biggest questions with us, think about subscribing. We have so much more to uncover, from the mysteries of dark matter to the search for life beyond Earth. Hit that notification bell so you don't miss our next journey into the unknown. A new perspective. So, we're back where we started, but with a totally new vision. The black hole is not a simple monster. It's not a cosmic vacuum cleaner. It is a fundamental engine of cosmic evolution. It sits at the heart of its galaxy not as a parasite, but as a partner, locked in an intricate dance of co-evolution that lasts for billions of years. The evidence is now overwhelming. Black holes anchor their galaxies. They grow with them. And through the messy, powerful process of feedback, they conduct the galactic orchestra. They use their energy as both a pruner and a gardener, using negative feedback to quench star formation and sculpt a galaxy into its final form, while using positive feedback to trigger the birth of new stars. They are the architects, the regulators, and the sculptors. This revelation forces us to rethink the very nature of creation and destruction. It shows us that they aren't opposing forces, but two sides of the same cosmic coin. The universe is a place of cycles and balance, where the energy released by consumption becomes the very energy that drives new creation. The fall of matter into a black hole can start a chain of events that leads to the birth of thousands of new stars. So, the next time you see a majestic picture of a galaxy, remember what lies at its heart. It's not just a monster lurking in the dark. It is the master architect. The unseen hand that shaped the spiral arms, that quieted the stellar nurseries, that ignited new star clusters. The most destructive object in the universe is also its secret, essential builder.